So I just want to include a nice picture of that town since Dune is involved in these studies. So yeah, okay, let's look at neutrino oscillation. So if you think about like what the neutrino particle actually is, so if you ask what the answer to that question is, I mean, personally, I would say that the actual real states are the states of the free propagation Hamiltonian, which is to say that the actual neutrino states are the mass states. But those aren't the things that we see in the detector. So whenever we produce or detect a neutrino, we detect them as these weird flavor states, which are superposition of the real physical states. And so that means, so in this cartoon up here, we make a neutrino with some flavor alpha over here, detect it with some neutrino with some flavor beta over there. And in the intervening space, they're propagating with some mass. That means that they have some e to the IE t over h bar phase angle that accumulates for each one of these. But since each one of these has different masses, those phase angles are going to accumulate at different rates. That means when you produce and detect these neutrinos, they aren't going to have the exact same state. There are going to be some quantum effects that change the states. And so that means that this new alpha and new beta are not the same. So you're going to get different actual physical state of your detector. You're going to get different flavor composition when you actually go to detect your neutrinos. And so that's what neutrino oscillations are. So what does it look like in terms of phenomenologically splitting down the parameter space? So really, this is the PMNS matrix. This describes neutrino mixing. And it can be factorized nicely into three simpler matrices. So here you have the so-called atmospheric matrix, the so-called reactor matrix, and the so-called solar matrix. So these are all named by basically the source of neutrinos that from which we learned the first things about these mixing angles and the mass splittings that go into making the actual values in these matrices. So today we'll basically go ahead and talk about understanding the basic measurements to get down these mass splittings and angles. Yeah.
Thank you. When we wrote this in other classes, we added like a Majorana phases matrix. Why are we not adding it now?
Yeah. Well, it's just physically unobservable with oscillations, right? So what the Majorana phases do is when you write out the effective mass for a particular flavor, you'll get different Majorana phase angles related to each one of the mass eigenstates. So that really just changes what the overall effective mass for each one of the flavors is. But since oscillations are only sensitive to the delta m squared, you don't really get sensitive to those angles. So they sort of just drop out of oscillations. Okay. So oftentimes we just don't even write it down. Okay. But yes, there is a Majorana term basically here if we do think the neutrinos are Majorana. Okay. Yeah.
Thank you.
Yep, thanks. So right, the parameters that we have to measure. So this is just thinking about if we're doing oscillations in vacuum. If we want to fully describe this this parameter space, we have basically three Euler angles, which describe the rotation between the flavor and mass bases. We have some understanding of what these are. These are 3 sigma ranges with current data. And then we also have 2 mass splittings. This is basically going to be 2 frequencies at which the oscillations happen. Here again, the 3 sigma ranges, and note that they are off by a factor of about 30. So that will be important in the next slide. And then there's also CP violation available when you have 3 or more neutrino species. We have some indication of what that might be, but we are still, we still really have to nail down this parameter. There's still a lot of uncertainty. That's a big range. And yeah, today we're going to talk about solar, atmospheric, reactor neutrinos, how we got the first measurements of these top 5 parameters. Tomorrow we'll talk about the remaining questions that we have. One is the glaring thing to think about is there CP violation in the leptonic sector? Whenever we see CP violation anywhere in nature, we always learn something, so we're incredibly interested in seeing whether leptons also give us another source of CP violation. The next is this question of theta 23. Is it equal to 45 degrees or not? If you look at the current range, 45 degrees lives right in the middle there. And 45 degrees is, pretty special. This is the angle that you need for basically muon and tau neutrinos to mix maximally. So, for instance, you would get complete disappearance of mu being produced going into nu taus. And if there's that equal composition of nu mus and nu taus in the nu 3 state, that would sort of point to some interesting underlying symmetry that should be reflected in upcoming models. So that will give a little bit of direction to phenomenologists making models in the future. So that's a question that we need, and we also need to know which state is the heaviest. Is this nu 2 state the heaviest, or is the nu 3 state the heaviest? This is the neutrino mass ordering, and this is very important since it a lot of downstream physics depends on which of these two mass orderings we live in. Like the double beta decay plots always separate out scenarios where you live in normal or inverted orderings. And we looked at yesterday the plots from the cosmic neutrino background also. And so really just nailing down which one of those from oscillations is going to help a lot of other aspects of neutrino physics. So those are the things that we'll talk about tomorrow. But for today, everything that we'll do today really just cares about two flavor oscillations. We have the ratio of these two mass splittings is something like a factor of 30. That's really convenient. That means that these two oscillations happen at different scales, so we can build different experiments which will focus on one or the other. Also in this two-flavor approximation, we can very clearly write down what the transition probability will be. So this is the so-called appearance channel going from one flavor to the other. That's proportional to just the sine squared of 2 times your mixing angle times the sine squared of this dynamical value, the delta m squared L over E. This is pictorially exactly what this looks like. So this is the disappearance channel. Here you give some specific baseline where this dynamic variable in the sine squared here basically equals pi over 2, so you get maximum disappearance of this flavor. This is the disappearance channel, which is going to be 1 minus the appearance channel, which is in red here. And exactly this wavelength is related to basically the wavelength equals 4 pi e over delta m squared. So this, in this way, the delta m squared is basically just the frequency at which the oscillation happens. And then the sine squared theta is the degree of appearance or disappearance that you get at the maximum oscillation point. Let's go ahead and actually talk about the physics experiments that learned this physics. And so we'll start with solar neutrinos. So pretty picture of the Borsino detector here. What is the story of solar neutrinos? So we know that within the stellar core, we have a bunch of nuclear processes that are fusing elements. We know what those processes are, and then we know that they all produce neutrinos. And so we can just basically look at the optical signal and say, the amount of light that is being shown from the sun is equal to the amount of energy produced by fusion in the core. We can put those in equilibrium. We can take into account all of the cross-sections for all these various nuclear processes happening in the core. And we can basically write down all of those processes that produce neutrinos, figure out their relative rates, and plot the total neutrino flux that you expect, which is what you're seeing down on the plot here on the bottom right. So there are 8 different processes, nuclear processes that actually produce neutrinos. And about 99% of the energy comes from this so-called PP process. That's from just primary proton-proton fusion, giving you a deuteron, a positron, and an electron neutrino. That unfortunately has a pretty low energy cutoff, so it's pretty hard to measure. The maximum energy that you get there is about 430 keV. But here at higher energy, you have multiple sources. These beryllium-7, PEP, boron-8, and AGP contributions all make up the so-called PP chain. And then there's also a CNO chain, which is another way of basically fusing protons into helium, which give you neutrinos from decays of nitrogen, oxygen, and fluorine. So this is the flux that nature gives us. This is what we have to study and discover oscillations and study the interior of the sun. So how do we go about discovering this? So this is one of the most interesting neutrino experiments that we have ever had. So basically, Ray Davis came up with an idea for discovering neutrinos from the sun by using a giant tank of dry cleaning fluid. This is a carbon tetrachloride solution, about 600 tons. And he built this underground in the SAIFR lab in South Dakota in the USA. So you see that this is the tank here. This is just a big pit that he filled up with water. Here he's swimming in that swimming pool. This water is just a veto to moderate any neutrons that are produced in these cavern walls. And the discovery here is very important. This won a Nobel Prize. So if you actually go to SAIFR, in LEAD, you can see a cross-section of this tank right in front of the open cut for the mine there. And so how does this experiment work? You're going to look at neutrinos coming from the sun. They'll capture on one of the chlorine atoms from the carbon tetrachloride. So that has a threshold of about 800 or so keV. That's going to produce an electron and an argon-37 atom. If you pay attention to the experiments that we've been doing, maybe your first intuition is to measure the kinetic energy of that electron. Of course, Ray Davis did something completely different. He was, by upbringing, a chemist, and then he came to Brookhaven as a chemist, and sort of forming a new group. And they told him, find something to work on. And he sort of just bumbled around thinking about the really interesting problems in science right now at the time, at around 1950 or so. And he came on the detection of solar neutrinos. He thought that this is a very interesting problem, that the sun is emitting this type of radiation that has not yet been observed at the time that he was thinking about these problems. But maybe we can have some chemical process that we can actually detect the effects of these neutrinos passing through your detector. Basically he has this carbon tetrachloride. When a neutrino interacts on one of the carbon atoms, it's going to make an argon atom, which is a noble gas. So it's not going to be very happy living in a liquid state. It's going to want to escape that liquid solution as a gas. So he basically devised some double filtration system to both move around the liquid solution and the gas solution. So there's two different circulation systems here that interface right here at these eductors, that's the word, sorry. And so at the interface between the gaseous and liquid circulation stage, you'd basically bubble in little bubbles of helium and introduce it to this carbon tetrachloride solution, and similarly move the carbon tetrachloride solution to the bottom with aspirated helium bubbles in it, and then just let the helium bubbles float up through the tank. Continuing this double circulation process several times, you are basically going to get every argon atom that is somewhere in the tank next to a helium bubble. The argon atom is going to get eaten up by the helium bubble since it wants to be in a noble gas state. And so once you're here after step 2, you get a bunch of gas bubbles coming up to the top of this tank, which have both helium and captured all the argon from this tank out. And it goes next through step 3. This is a condenser at about -40 centigrade. And that's basically just to freeze out any of the remaining carbon tetrachloride that may have gotten soaked up by the bubbles. So once you get a gas solution up here, this is going to be completely composed of helium plus a few argon atoms that you trapped from neutrino interactions. And then you send it through this line, and going to step 4, this is a charcoal trap. So charcoal was cooled down to 77 Kelvin with liquid nitrogen. If you look at 77 Kelvin, compare that to the freezing point for the melting point for different noble gases. The argon is going to be still a gas. Is going to be a liquid at 77 Kelvin, but the helium will be a gas at 77 Kelvin. So that means that the helium is light, so it has a lot of kinetic energy. It can sort of diffuse through this charcoal trap. But the argon is heavy at 77 Kelvin. It doesn't have enough kinetic energy. It sort of just deposits out on the surface of this charcoal trap and sort of gets trapped there. And so when you exactly just continue cycling through all the helium here in this part of the gas circulation system, you just have pure helium. All the argon, few atoms get trapped in this charcoal trap. And so the last step, step 5, is, well, just take this charcoal trap, heat it up, and have all the outgas go into, get collected into this contraption, which has a proportional counter up at the top. Argon-37 is radioactive. It decays on about a 30-day time scale. So if you just count the number of radioactive decays as you see as a function of time, then you can explicitly see the number of Argon-37 events that you trapped in the charcoal. And then, of course, use that to infer how many interactions were actually happening in your experiment. So this is how neutrinos were discovered coming from the sun. It's a great chemistry experiment, very interesting. And this is sort of what the status of the field looks like. So Ray Davis had discovered neutrinos. The problem is the number of neutrinos that you just saw was not quite consistent with what you see in experiment. So the black line up here, this is actual data constraints that we have. Up here, we had not yet discovered neutrinos from the sun, and so we just had limits, until finally in 1968, Davis saw his first actual real detection, and sort of the experiment leveled out here. There's also uncertainties in the theory here, where you're discovering the PP and CNO cycles for the actual fusion cycles within the sun for making neutrinos. There were some uncertainties in the cross-section here, and then they finally developed the field enough to be able to put an uncertainty bar on what the flux is. And here, coming out in 1970 and really going through the 1970s decade, they were really seeing that the flux of neutrinos is about a factor of 3 lower than what we expect. This is a problem, so where do we go from here? By the 1980s, it was very clear that this experiment that Davis designed was right. It is measuring what we expect. The efficiency for collecting Argon-37 is consistent with expectations. So really, we need to study this problem a little bit better. It looks like an actual real anomaly in physics to pay attention to. One question that you might have is, well, 99% of the solar flux comes from this PP reaction. This guy up here, which has an endpoint at about 430 keV, which is below the chlorine threshold. So Davis had absolutely no sensitivity. He was actually mostly measuring this boron-8 flux. So the next question is, maybe we just have to measure this lower energy flux. Maybe that flux is, roughly consistent with expectations. Just these lower flux, higher energy fluxes are just all off because we get the nuclear cross sections a little bit wrong. We get the temperature in the stellar core a little bit off, and that, really adjusts the high energy components that you see. And so we basically had a new version of the Davis experiment, still sort of a radiochemical separation process, using gallium instead of chlorine. And if you look at gallium, the threshold for neutrino capture is down here at about 230 keV or so. Much lower than the PP threshold. So this experiment was dominated by these PP neutrinos. And basically the same story. So we have solar neutrinos interacts within this gallium target. Eventually, it will get regularly flushed with some chemical and be separated have these germanium-71 radioactive isotopes separated out. We look for the decays of those. And if we look at data from this, these experiments started in about 1990. Both SAGE and GALAX started consistently seeing that they were seeing, a deficit in the number of neutrinos relative to what you'd expect. So this blue up here, this is the expectation. This is what comes from the standard solar model. And then this golden band, this is the average of the SAGE and GALAX experiments, the gallium experiments that we have. And so we're averaging out to just about 55 to 60% survival probability for these neutrinos. That's a little bit interesting. So both the PP neutrinos from SAGE and GALAX from the gallium experiments and Davis's measurements of mostly boron-8 give you a deficit. But these two deficits are different numbers. So nature's throwing all sorts of crazy things at us. We don't really understand this. Maybe there's some energy dependence. That's what will end up being the question that will be. We're looking at oscillations right now. But we didn't quite believe that, since saying that neutrino mass is non-zero was a revolutionary idea. So you need a lot of evidence for that. So to build up that evidence a little bit, first let's try to calibrate your detector. So we know that these gallium atoms will absorb neutrinos at low energies. So let's just put a radioactive source. So chromium-51 will decay by electron capture and give you a neutrino with a monoenergetic 746 keV. So, okay, you can just measure the cross-section for neutrino absorption, or estimate theoretically the cross-section for neutrino absorption on gallium, and exactly just look at the rate of germanium-71 produced by these neutrino interactions, given the flux of neutrinos that are coming off from your calibration source. And this is exactly what we get. So they see that there's maybe a little bit of deficit, maybe about 10% or so, but nowhere near enough to explain the solar neutrino anomaly that we're seeing. And if you heard about, surely you heard about sterile neutrinos in the first week, the best experiment is sort of a successor to these experiments down here, which is really improving your systematic errors. And this is basically how that gallium anomaly was discovered in sterile neutrinos. So this is a nice connection there to current uncertainties in oscillation framework and the oscillation picture. Okay, so we have these two fluxes of neutrinos at different energies, and they have different survival probabilities. So next we might want to do, instead of these radiochemical experiments, we might want to go to standard neutrino detectors and see actual interactions of neutrinos in real time, things that we can look at in event display. So Super Kamiokande was the first detector to really do this. Kamiokande 2 with lower mass looked at this with less precision. And so the interaction channel that we have here in Super Kamiokande is neutrino electron scattering. We don't get inverse beta decay in the water this time because inverse beta decay only has interactions for antineutrinos. Solar neutrinos give you actual neutrinos, not antineutrinos. And so we can use these electron scatterings events to basically estimate the boron-8 flux of neutrinos. These are the higher energy neutrinos spit out from the sun. And the nice thing about electron scattering is there's this correlation between the electron angle and the neutrino angle. And so the Super Kamiokande experiment leveraged that to basically point back to the sun and separate out signal from background. So this is looking as a function of the angle between, well, the cosine of the angle between your measured electron and the sun. And you can see that there's this rising distribution here, that those are your actual solar neutrino events. And then you have this flat distribution, which come from just random radiological backgrounds in your detector. So yeah, great way of estimating these backgrounds with ways to constrain your backgrounds with real data. And yeah, so just saying, Super K had a threshold of about 6.5 MeV, and saw a survival probability of about 35%. So pretty consistent with what Davis saw. The next step, what really resolved this problem was the SNOW experiment. So this is similar to Super K. This is going to be a water Cherenkov detector. The only catch here is SNOW was a heavy water Cherenkov detector. So that will be important on the next slide. So the total, how this experiment was made. So what you're seeing here, this is a basically big acrylic sphere. So you can basically separate the material on the inside here and the outside here. So inside you have about 1 kiloton of heavy water dropped down into this acrylic sphere. And on the outside, you will have light water. And then in here you have something like 10,000 PMTs watching and looking into any light produced in neutrino interactions in this inner or outer volume. You can, with Cherenkov ring imaging, you can estimate the vertex of where these interactions happen. You can decide whether it happened in heavy or light water. And so all in all, this light water region becomes basically a buffer region. And you have a nice fiducial volume here of heavy water surrounded by a buffer light water Cherenkov detector, and also an outer veto shield for cosmic rays. So yeah, this experiment will give you vertex information and calorimetric information for all of the interactions happening in the heavy water. So what, this is what really, opened up the solar neutrino, solved the solar neutrino problem. So in heavy water, you have multiple interaction channels. That is what is key. So you can have, now you have a neutrino scattering on deuterium. Deuterium is a more complicated nucleus than just hydrogen, just a proton. And so you can get this neutral current interaction where the neutrino just splits up the deuterium, gives you a neutron and a proton, and that gives you just a gamma in your detector, so you can measure that, and And since this is a neutral current process, this will not oscillate. All of the flavors of neutrinos will interact in this channel. Then you also have the charge current interaction, where this NUI now comes in, hits the deuteron, breaks up, but does an isospin flip, makes two protons in the final state. This will give you an electron in the final state, but with different energy from the neutral currents. And this is going to oscillate, since only the NUI can do this. This is a charge current process. And then you also have electron scattering, which all flavors participate in, but with different concentrations. It's still mostly the electron neutrinos which are making this interaction, which we talked about yesterday from the different cross-sections for different flavors for this process. Okay, so we have these three great interaction channels. We can just go look on this plot, this wonderful, beautiful data plot that shows the calorimetric energy that Snow saw in data, along with the expectations for what the shape should look like for these three different interaction channels within for neutrinos within the detector. And you can just do a fit to this data of this charge current distribution here. You get higher energies than charge current since all the energy is visible in the final state. And then you have a lower energy neutral current component down here, and then also a more broad electron scatter component. And if you do fit to this data and work out the normalizations of each one of these three components, you get something like this. You understand what the fluxes of different weights of different neutrino flavors are. So this right here, this is the easiest to see. This is the charge current flux that is that's from the NUI charge current interaction. So that just gives you a single flavor of neutrinos. And so that gives you just a vertical line. You're measuring the electron flux, but not the mu and tau flux. And then the neutral current here is an equal component of each of those three fluxes. And so that's going to give you some sort of diagonal band. And you also have another angled band coming from electron scatters. If you look at the where these three different fluxes that Snow was able to measure line up, they basically come all right at this point here, which turns out to be exactly equal to where the standard solar model expectations are. So here's really the answer. This is what is going on with oscillations. We know that we see that the charge current flux is a little bit less. It's a factor of 3 less than expectations from the standard solar model, but the neutral current flux is basically right on target. So the total neutrinos are the same as expected from the solar models. It's just the NUI flux is down by a factor of 3. That's what gives us oscillations. And yeah, so it's worthwhile just sitting down and thinking about this survival probability. Yeah, so this is just the Hamiltonian for two-flavor oscillations in matter. I was thinking about doing this on the board, so I think I will just continue to do it through slides. But yeah, basically you have this vacuum component. The difference in energy basically just comes down to the delta m squared divided by the 2 times the energy. So this is basically the Hamiltonian that you have in vacuum. And then if you add the matter component, just coming down from differences in interaction rates for neutrino electron scattering for different flavors, you get something, a term that just is attributed to the electron component of the electron neutrinos, which basically comes down to the interaction probability, which is this GF, the coupling for the weak force, times the number density of the electrons, the thing that is actually making the asymmetry between electrons and mu/tau. And also just throw in an energy factor for to conserve units. And if we look at the low energy regime, at low energy, basically this term goes to 0. And so we just have this vacuum term here. So that means that now the physical states of the Hamiltonian, the actual particles that are being produced and propagating, are going to be exactly the free Hamiltonian. The free propagation states are the Hamiltonian, that is to say the normal mass states. And that happens when this energy is less than delta m squared over root 8 GF and E. So that is basically just meaning, this this delta m squared is greater than this factor over here, and that gives you the energy regime. And if you look at that, then you're just going to have, standard an oscillation pattern. If you work out the baseline with the delta m squared that we now know after the fact, that oscillation baseline is something like 100 kilometers. And so, of course, the distance from the sun where the neutrino is produced and where they're detected on Earth is much greater than 100 kilometers. So this survival probability basically just thermalizes, and this dynamical variable basically just averages out. The average of sine squared gives you 1/2. And so the survival probability for electrons is just this 1 minus a half sine squared 2 theta 1 2. Now after the fact, we know that theta 1 2 is 34 degrees, so we can plug this in and see that this survival probability should be about 57%. So we should measure 57% of the neutrinos as electron neutrinos in our detectors here at low energy, which is consistent what we're seeing with PP neutrinos. If we go up to higher energy, this is basically the opposite scenario where basically we can forget about the vacuum term and this matter term completely dominates. So here, the states of the actual propagating states of the mass states in this dense matter medium is going to be basically equal to the flavor states, because this flavor process is driving the asymmetry, the differences in energy levels between each of the neutrino states. So we can actually just say that the electron neutrino state in matter, this is a typo here, this should read nu e, is just going to be equal to the higher energy state, the nu 2. And so, well, you're actually producing through nu e production in the solar core, you're actually producing a mass eigenstate, which means that the neutrinos aren't actually going to oscillate. You're just going to have a steady mass eigenstate that travels through the sun, reaches the Earth as this nu 2 eigenstate. And then we just, basically write out this nu 2 eigenstate as some component of nu e and nu mu for traveling in vacuum in low density media like the Earth where it is detected. And then basically you just take the contraction of the nu e state on this nu 2 state, which the neutrino pulse arrives at Earth at, and you see that the survival probability is just the sine squared theta 1 2. So if you go to high energies and plug in the theta 1 2 equals 34 degrees, you see that this sine squared, this survival probability term is just 31%. And so that is basically what gives this turn down behavior that you see as you go to higher energies. The problem is, where does this turn on actually happen? That all comes down to where the energy scale is relative to this factor here. You can, this basically says that solar neutrino experiments on their own don't really have a great ability to measure delta M squared with these types of methods. So we have sort of this order of magnitude or so uncertainty of where the actual turn-on transition regime between these two survival probability scenarios is, which means that we don't know where this turn-on is. It could be earlier or it could be later. All that our data basically tells us is what the values of the sine squareds are. So we go out and actually make a contour. This is what the parameter space looks like just using solar neutrino data in the early 2000s. This is taking Davis, gallium, SNO, and super K data and just looking at where the oscillation parameters lie. And here we get a sensitivity that is decent in the angle here, but actually kind of poor on what the mass splitting is, what the delta M squared is. And that's because we don't really know this transition region between high and low survival probabilities. So, how do we fix that? The way to fix this ended up being the Camland experiment. And so this was sort of a clever idea. If basically just have a liquid scintillator detector that is looking for reactor neutrinos in Japan. In Japan, there's a ton of reactor neutrinos, but they're all sort of centered in populated areas, which are like here along the coast. If you go to the Japanese Alps, where the Camland experiment is, there aren't any nearby nuclear reactors, so there's really just a ring of reactors at about 180 kilometers plus or minus some band. And so you basically have a bunch of neutrinos shot at your detector with a common baseline. And so that from there, we can basically look at, measure the frequency of oscillation in terms of L over E, and use that to determine with good precision what the delta M squared is. So here's the actual data spectrum that they have. So here is the best fit with no oscillations that they might expect. And this blue line here is the best fit with oscillations, which matches their data beautifully. And if you go in and basically rework this plot instead of just looking at the prompt energy that you have, if you look at turn this into the dynamical variable L over E, you see a very clear oscillation pattern here, and that frequency of that oscillation is just going to give you your delta m squared with good precision. If you superimpose the contour that CAMLEN is able to produce on top of the SNO and SK contours, you see that they're quite complementary. So SNO and SK give you good measurement of this angle here, but CAMLEN gives you, through the frequency, a very good measure of the delta m squared. So this is a nice demonstration of the complementarity of these two approaches, and by having these two very different approaches to measure oscillations on the solar baseline, we can get a more complete picture of what is going on. Yeah, so where do we go from here? The next step for, we've seen oscillations in solar neutrinos, but we would like to get a more precise measurement of what the flux looks like. This really comes down to the Boraxino experiment, and the whole thing about Boraxino was just having absolutely stellar background radiation control, which they really got by having, instead of this sort of acrylic onion structure like SNO had with an inner volume of active material where your interactions happen, and then outer veto layers. Here, Boraxino has two. And so in the interior volume here, you'll have a liquid scintillator. Out in this middle volume, you will have some chemical composition that has, mineral oil with some light quencher, this dimethyl phthalate. So any light that is produced in that volume basically gets eaten up. And then out here you again have just some mineral oil, which is radioactively inert, but should not give you a lot of light. And then you have, again, just about 2,000 or so PMTs mounted on the surface here, and an additional surrounding water tank for vetoing. And this is what the fluxes of solar neutrinos looks like coming out of Boraxino. So they're looking at electron scatter events here, and the red curves that you see here, these are all of the different 5 processes from the PP chain of solar neutrino propagation, along with the different colors, and the black distributions are various radioactive backgrounds. The PP flux, this is right here, this is the lowest energy flux, very difficult to see without radiochemical means. And you can see that you're separating that out from this green carbon-14 background with difficulty. So they were able to maintain carbon-14 concentration of about 100 times 10 to the minus 18 for parts of carbon-14 per carbon-12. So that really phenomenal radiological control is what allowed them to actually measure these PP neutrinos. And they also were able to discover the CNO chain, which produces something like a couple tenths of a % of the neutrinos in the sun. And yeah, we have new detectors coming online. So Javier mentioned this. So we are also seeing now 7 interactions from solar neutrinos from the boron 8 flux. So these are just standard dark matter, liquid xenon dark matter TPCs. And both the Xenon N-ton and Panda X 4-ton has seen this process at about 2.5 sigma. So put those together and you get 3 and some change sigma. And so you see here the boron 8 7s that we're measuring here is the pink distribution here. So you see a nice little excess over these green and yellow backgrounds. And so here's just another interaction channel, which is giving you, here you're seeing some measurement of what the boron 8 flux is. The best fit from SNO is just this little tiny error bar up here. But now we have a new detection scheme and a new interaction channel, which is seeing at lower precision a measurement in the same parameter space. So yeah, where is the future of solar neutrinos going? So really we want to understand this upturn really well. So we have these measurements from sort of online direct imaging of electrons and Cherenkov detectors and so forth above about 10 MeV. And then we have these radiochemical methods and Boraxino looking at the very low fluxes at less than an MeV. So what does this oscillation probability look like? Which of these scenarios do we live in? So that is one of the open questions. And then I also said that we have 8 processes that are making solar neutrinos in the solar core. We have measured all of them except for this HEP process. So the problem here, this is actually giving you the most energetic neutrinos, but the flux is just incredibly low. It's just about 1 part per million of the neutrino flux is produced in this HEP flux. So these are the 2 things that we really want to understand. We want to discover HEP and measure this turn on. One way that we can do this is to build the Dune experiment. I introduced Dune yesterday with supernova neutrinos. And this is just a measure, again, a picture of their vertical drift module. So this is a 17 kiloton TPC, looking at using argon as a detection medium. So you will see charge current interactions in the detector. Just a little bit about what solar neutrinos look like in Dune. So this is the cross-section for different interaction channels in argon. You see that the NUI charge current interaction on argon dominates, so that is what is going to give you most of your events. This is what you're going to see in your detector. So you will see an actual electron track with a few de-excitation gammas. And then just moving on to what the physics Dune can do. This is estimate of from a theorist of looking at what the boronate charge current interactions will look like and HEP charge current interactions will look like. So we can really precisely basically measure this knee in the Dune experiment and make a detection of this last flux of solar neutrinos. And then also, since we are looking at a charge current interaction in Dune, we can get very good estimates of the neutrino energy and get very precise measurements of the survival probability down to maybe about 5 MeV as a threshold. So we can probe a lot more of this upturn and make some statement about whether this standard solar oscillation parameter, solar oscillation probability is accurate, or maybe there's some extra physics going on. Yeah, so that is it for solar neutrinos. So I'd like to go on to atmospheric neutrinos. Yeah, so these are just produced by showers in the upper atmosphere. So protons hit nuclei in the upper atmosphere, make pions, which decay and give you muon and electron neutrinos. And this is the other sample that proved that neutrino oscillations exist, mostly with the Super Kamiokande experiment. And so these atmospheric neutrinos are coming at us from all directions, and at these low energies, the neutrinos can pass through Earth quite happily, and they can interact in your detector with various with neutrinos coming from different angles, which means that the neutrinos have different baselines on which to oscillate. And so we can basically use the calorimetric energy information from the detector plus the directional information to get L and E estimates, and again observe this L over E dynamic behavior. This is what the flux looks like. So this y-axis is not the flux; it's energy squared times the flux. So the flux falls very, very rapidly, and we have basically a typical energy of a atmospheric neutrino of just around a GeV. Yeah, so really early history. So atmospheric neutrinos were actually discovered before solar neutrinos back in 1965. This was in a gold mine down in South Africa, and they basically have these two parallel sets of 3 scintillators that are stacked on top of each other. And they're basically looking at muons that are going through these 2 sets of scintillating panels at the same elevation, at the same vertical position. And if you see 2 panels light up at the same time, you know that you had a muon coming in from that's going horizontally. Atmospheric muons going horizontally would not have a chance to make it to this detector, but you can see muons from atmospheric neutrinos just fine. And so this was how that was discovered. This was also discovered by Frederick Reines, also the guy from the first detection of the neutrino, so pretty good career for him. He made the discovery of the neutrino, and then he turned around and made the discovery of natural neutrinos, astroparticle neutrinos. And so that was in the 60s. If you go into the 1980s, we were starting to get some hints that oscillations were happening. So this is looking at the top from Kamiokande 2 data. And you see that, yeah, maybe the muon component is disappearing a little bit, and the electron component is maybe right on top of where you would expect. But then you also had the Freyjus detector underground in the Alps, which is basically seeing things that are consistent with flux expectations. And so this was a little bit of a mystery why these 2 experiments were seeing different things, but they were both at low statistics, so we really just need a large detector to really resolve that problem. And of course that the answer for how to solve that problem is Super Kamiokande. So this is looking at the first analysis using just 535 days of Super Kamiokande, and you significantly bolstered statistics. See a pretty clear, in hindsight, oscillation picture. And so what we're looking at here, so these top 2 plots are electron-like neutrinos. So you're seeing these fuzzy electron rings over here in and you're selecting those events and putting them in this plot. The left plot is these are low momentum particles, electrons that you see, and here you have the high momentum particles. And you see that the electrons are, more or less consistent with expectations. Maybe you see a little bit of appearance, actually, of electron neutrinos. But then when you go to the muon-like neutrinos, at low energy, you start to see this deficit at very large angles. And then at high energy, you see a deficit at high angles, but this disappearance probability basically turns on later. So they will only oscillate at longer baselines. And so these lower momentum are, more free to oscillate because they're at a lower energies, and L over E is the dynamic variable you care about. But then these higher energy muons also tend to oscillate coming at higher energies. And so this is really consistent with the oscillation picture. These are the oscillation contours that Super K was first able to place. So yeah, this is the 90% confidence region that they were first able to place. This is consistent with the modern best fit right around here. Kamiokande up here, initial data was just a little bit high, but not terribly inconsistent. And yeah, so this was now in hindsight a pretty clear oscillation picture. It makes a lot of sense. It's a nice story to tell. But right after the fact, there was just a lot of uncertainties looking at neutrino scattering at a GeV. So there's a lot of work put into making sure that this Super K signal that we're seeing is actually oscillations and not some uncertainty in either the flux or the cross section. So I'd like to talk about just a little bit about how we did that. So the first is working out what the neutrino flux actually is. So here there are two parts of, so yeah, let's first work about, we care about the primary protons and pions that are produced in the upper atmosphere. So we want to basically go up into the upper atmosphere, look at the flux of primary protons that are incident on Earth, and those will subsequently interact in the upper atmosphere and make pions, which will decay into neutrinos. So we have this balloon experiment here about 6 meters tall that had basically a payload of a high energy experiment, high energy physics experiment that went up into the atmospheric, into the atmosphere about 35 kilometers of maximum altitude, and had basically a tracking system here where they were able to see protons coming in and time of flight chamber to be able to select between different particles to know that for a specific energy, this particle was moving pretty slowly, so it was a proton, or is moving pretty fast, so it was a muon. And then we have a calorimetry here to just measure the total energy produced by these particles. And so this whole contraption is able to basically select out different particles with different energies and measure those fluxes. And this is the data that we're seeing. And the expectation that we see here, really this low dotted line is what we expect to match with the data. And we see that both primary protons and primary helium nuclei, so alpha particles, are meeting expectations from this experiment very, very well. So our initial estimates for these primary cosmic rays entering the atmosphere agree beautifully with our expectations. So this is not what is causing the Super Kamiokande oscillation signal. So there is one cross-check that we can mark off. Yeah, so the next is, okay, so we know what the proton flux is in the upper atmosphere, but do we really know about the probability for proton nuclear interactions up in the atmosphere to spit out pions, which will ultimately give you your neutrinos? So we want another way to constrain that, to constrain the cross sections for making pions in proton nuclear interactions. And to do that, you would basically go to an accelerator. This is the HARP experiment, where we have high energy proton beam incident on a target here, which goes through a few Cherenkov counters and a few magnets and calorimeters. And using this, all this data together, you're able to basically look for the signs of particles, the momentum of particles, the energy of particles, and therefore the mass of particles, and be able to work out the number of pi plus, pi minus, and other mesons that are produced in this target from proton interactions on different nuclei. And this is sort of a look at what HARP parameter space was able to do. So they were looking at a very large range of primary momenta, anywhere from about 1 to 1,000 GeV of momentum on the x-axis. And this is the momentum of pions that are produced in those interactions, again going from about 100 MeV up to the total energy of the primary. Just looking at covering this parameter space, HARP sees that actually we are actually understanding these pion production cross sections also pretty well. So this is also not the problem that Semiconductor is seeing. And this, I'll just say that this method is also continuing with the NA61 and the NA61 Shine experiment and emphatic now in the current day to not to really understand the atmospheric neutrino flux, but to look at the flux of neutrinos in accelerators for accelerator-produced oscillation studies. Yeah, so that basically says that the neutrino flux that we're estimating for Semiconductor is roughly on target. So we're producing we are producing the Earth is seeing the right amount of primary proton flux as we expect, and those primary protons are producing pions at about the right rate as we expect. So the next thing that we really have to do is think about this number event calculation is now cross-check the cross-section. So this, when Semiconductor data came out, we started just hacking into old bubble chamber data from the 1980s, which give you really beautiful pictures of neutrino interactions. So here is a meson producing a pi proton and a pi plus. So the goal here is to use the look at the number of events that you're seeing in these bubble chambers compared to the flux of those interactions, and propagate that to our expectations for what we would expect in Semiconductor from our constrained flux of from our constrained atmospheric flux, and see if that is all consistent, or if that could somehow explain the oscillation type anomaly that Semiconductor was seeing. And this is early data in preparation for the Semiconductor detector turning on and seeing atmospheric neutrinos. You can see that the uncertainties in this sort of GeV range, which is where most of the atmospheric neutrinos lies, are sort of on the order of 20%, and there's not really a lot of energy dependence here. So you'd expect if there's really a lot of this uncertainty here looks more like a flat uncertainty rather than something involved with the shape, which you would need to explain the oscillation signature. And so this cross-section uncertainty also does not look like the solution. So it looks like a bona fide oscillation signal that Semiconductor is seeing. The last check is to just see this in some sort of man-made neutrino flux, this same oscillation behavior. Since it's convenient that you have disappearance of muon neutrinos, muon neutrinos are very easy to make at an accelerator. Again, just hit protons at some target, and that will produce pions, which will decay to new mus. And then you can do this at some accelerator here in Japan at Keck, and shoot it over now to Semiconductor, and again just look at this oscillation signature now in an accelerator beam. And this is the data that this K to K experiment doing this looked at. This is oscillation data in the Semiconductor detector constrained with some near detector data. So this blue solid line here is the expectations with no oscillations. And then the red here is the best fit with oscillations compared to this black data. And so you see again that there is pretty clear evidence for an oscillation signature here. This is the level of contour that K to K was able to accomplish compared to data from Semiconductor. So the measurement is worse, but this is confirming with a very well-controlled neutrino flux that the cause of this signature in Semiconductor atmospheric data is actually oscillation data. It is actually neutrino oscillations. And yeah, so the last, I only have about 5 minutes left, but just really quickly talk about reactor neutrinos. This is coming up, so we resolved the solar and atmospheric neutrino anomalies at around 2000. So the Diabay experiment came out on the scene with first data in 2012. So this is about 10 years later that we're getting this last mixing angle left that we have to measure. And this was using reactor antineutrinos. So this is at the Diabei reactor in China. There were 3 sites of reactor cores here. And so basically, you will measure the neutrino flux and cross-section in some scintillator detectors here and a near detector, both by these 2 reactors and another near site here by this reactor complex. And then you also have a far detector, which is measuring your oscillated signal here a couple kilometers away from these reactors. And so again, like the K to K experiment, you'll have near and far detector data and be able to basically look at the ratio to look for direct evidence for the oscillation signature. Reactors produce antineutrinos, electron antineutrinos, so the perfect detection mechanism is inverse beta decay, so you'll need something with a lot of hydrogen in it to build your detector out of. Your options are water Cherenkov, basically, or liquid scintillator. These neutrinos are pretty low energy, so we'll go with liquid scintillator because it has higher light output. And so what you're seeing here is a specific unit of their detector, and it's basically 20 tons of liquid scintillator with an outer veto region monitored by several PMTs. And each one of these 4 detectors that they use in their far detector, and each one of their 4 detectors in their near detector complex are all exactly the same. They're just making 8 copies of this one unit here and putting them 4 up here, 2 down here, and 2 over here. So that using the exact same detector everywhere really reduces your systematics because they are all expected to operate in the same way. And so yeah, the first results. This is this was in 2012. This came on the scene sort of unexpected. We had not seen evidence of this reactor mixing ever, so we had thought that this would actually be a pretty small effect. But it turned out for the maximum oscillation probability turns out to be relatively high, about 9%. And we see a clear signature here. This top histogram here is what you would expect in your far Hall, given the propagation of your neutrino flux that you see in your near detectors. And then this black is the data that you actually see. So you see a clear deficit right around this energy, which looks like just a little oscillation wiggle. So if you look at the ratio here, you see a little dip right at that specific energy, which looks a lot like an oscillation signal. Yeah, so aspects of this signal that they have here, they were able to get incredibly pure inverse beta decay samples, so over 95% was signal, just a small little contribution from background. And the effect was overall small. It was just integrated over the full spectrum, just a 2.5 disappearance effect. But they were able to observe this at 5.2 sigma, given their small backgrounds and good energy resolution with the scintillator looking at this L over E pattern. And yes, and they do a near over far fit. Yeah, so I think that is it for summary. So just working out the basics of the oscillation framework, we have 3 mixing angles and 2 delta M squareds to really measure out. And natural sources of neutrinos were really driving this. So they measure the 2 delta M squareds along with the theta 1,2 and the theta 2,3 Euler angles. But then that last theta 1,3 came down in 2012 from the Diabei experiment. And yeah, this it was all like a very interesting story that happened, was being resolved in this 2000 to 2005 time frame. And right now we're sort of working out, we're in a sort of similarly interesting time frame where we have a number of accelerator-based experiments coming online, which will similarly answer the few remaining problems that we have in oscillation physics, like the neutrino mass ordering, delta CP, and maximal mixing for theta 2, theta 3. So that's it. Thank you.
Questions?
So at the very beginning, you have shown the plot of the ordering of neutrino masses and the composition.
Right, yep.
And there is like a colored, yeah, there's this red like curve colored. Is this like a PDF of the angle, the reddish thing?
Yeah, it's exactly the composition of the flavors in each one of these mass eigenstates.
But like
Yeah.
the wiggly is like the PDF of like between 0.71.
Yeah, of course, there's some
and-
uncertainty in
Right.
the breakdown, so that's trying to reflect that.
Okay.
Yeah.
Thanks.
Yep.
Okay, doesn't seem we have questions at this moment, so thank you again then. Now we'll have Luca talking about light dark matter in accelerators. Please go ahead.
Okay, can you hear me? Can you hear me? Yeah, okay. So, this is our last talk on light dark matter, and today we will finally see the missing energy and missing momentum experiment that are maybe the latest coming to join the search for this light dark matter in terms of technique to search. So last time we saw that beam dump experiment, dumping this very large amount of charge on a dump can achieve good sensitivities in both the visible and invisible decay scenario for dark matter. But I think that did not say is that this technique has a drawback, in particular for the invisible decay scenario, because there, if you want to use a beam dump experiment to detect light dark matter, you have both to produce it in the dump and then to make it scatter on a detector. That is what, for example, BDX does. And therefore, basically, you're asking for two very rare processes to happen. So you have a production, which is mediated by a dark photon, and so scales as epsilon to the second. And the scattering cell, again, is an elastic scattering mediated by a dark photon, so a rare process itself, scaling as epsilon to the second. So at the end of the day, the number of events that can expect a beam dump experiment searching for light dark matter scales as epsilon to the fourth power. So this means that, for example, you have your experiment and you reach some part of the parameter space and you want to go down by an order of magnitude, you need to acquire 100 times the statistic if you are thinking of a scenario possible to skip the second part of the process. So do you really care to measure, to detect the dark matter scattering in our detector? And the answer comes with the so-called missing energy technique. Here the idea is a bit different. So you have also in this case a thick target, so a target when you completely degrade the energy of your incoming beam. But now it is an active target. That is to say, it measures the energy, so an active beam dump. So the idea is this: you have your beam, you measure before coming to the target its energy, you measure the energy deposited in the target by the particle, impinging particle, and then you look at the difference between two numbers. If the difference is large, it may be that part of the energy has escaped in the form of dark matter particles. So this is a very simple scenario for this kind of experiment. And now you are limited in rate. You cannot just dump high current on your detector because you have to tag every single particle. So you have to give the time to your detector to see the particle which is incoming, measuring its energy, then the active target, and this means that you are somehow limited in rate, and also you need a particle beam which is capable of providing particle one at a time, which is not always possible for accelerator. For this kind of experiment, the signal scales now as epsilon to the second, so better than the you gain a factor epsilon to the second to the beam dump, but now you have to face many backgrounds because obviously we saw that for example, in an automatic shower, you produce many standard model particles which are themselves very penetrating, for example, muons, which would escape the detector, and you will have a signature which is similar to what of a dark matter. So this is maybe a kind of background. Also, we produce hadrons and other penetrating particles, but also you may have contaminants in the beam. If you think that this particle is an electron and instead is a hadron, the hadron may interact inside the detector, maybe producing some meson, decaying neutrinos, and then your neutrinos fly away, bringing away a lot of energy, and again, this mimics your signal. So many challenges to face, and up to now in the world, the only experiment that is using this technique to search for light dark matter is Na64, which is an experiment using the SPS electron beam at CERN H4 line. So the experiment is located in the north area of CERN, and from this, the not so fancy name Na64. Because it is the 64th experiment made in North area. The E here is that is due to the fact that they're using an electron beam, and there is a parallel effort by the same collaboration using a muon beam that we will see in a few minutes, so to distinguish them Na64E and Na64 mu. The sketch of the experiment is this one. So the active target, the dump itself, is this small part here. All the other, which is an electromagnetic calorimeter, as we will see, all the other components of the detector are just there to be sure, for example, that the particle that is coming is really an electron with 100 GeV, and nothing else is escaping from the calorimeter. And so to veto all the standard model particles that may be produced and escape from vehicle. So from upstream to downstream, you have a spectrometer composed of some tracking stations, which measure the position of a particle, a magnet, again tracking station, and you can measure the momentum of impinging particle, a synchrotronation detector that, as we will see, allowed to distinguish from electrons to hadrons, and then, after vehicle, a very large hadronic calorimeter to stop all the hadronic particle produced in vehicle or coming from the beam. So this is the general sketch. Here you have a picture, which is this experiment are not really nice to photograph because they are very long, and here you can see this is the target is here. This one is the module of the hadronic calorimeter, and this is the magnet that bends the beam to measure the momentum of the incoming electron. If after all this part, there is also another magnet, because if you produce muon in some part of the chain of the detector, for example, a pair of muons, you can use these muons, divide them with a magnetic field, then you have a tracking station, and you can do some physics with these muons, but I won't talk about this part of the experiment. Okay, so first of all, I told you this experiment is at SPS, which is the same facility where we lost, for example, SHIP, and SHIP we will use a 400 GeV proton beam. So this is the kind of particle you can find in SPS. So from this particle, if you want to use electron, you have to produce electrons, and to do so, the technique is this. So the 400 GeV beam from the SPS impinges on a target which is T2 target of a north area, and from this interaction you produce many particles, hadron, neutrals, electron and positron, and many gammas. And after the target you have some sweeping magnets that bends all particles that are charged, and only the neutral particle goes in a straight line, and within neutrals the main component are photons. Then there is the so-called X-tax, which is just a shielding that has some holes in there, so you can select the kind of particles and then depending by momentum. But we are interested in just the straight going trajectory for photons, because we have here a LED converter, and the LED converts photons in pair of electron and positron, and finally you have your electron beam. Obviously, you can understand that all this change, result in the fact that you may be, for example, some hadron neutrals, which are produced here, that are not bent by the magnet, and then they decay after the magnet in some particles that are contaminant of the beam. So this is basically what happens in this kind of not primary beam, and the result is that you have a contamination depending on what particles you have and you want to operate with. So for example, if you want electrons, you have this contamination, and this is the number of hadrons per number of electron impinging on your experiment, and you can see that at 100 GeV, which is the operation of Na64, we have order 0.3% hadrons per each impinging electron. and this is something that has to be accounted for. And to eliminate these contaminants, the first part of the detector, which is called also the upstream part, is responsible of the particle identification. And we will see now the components of this detector chain. So the tracking station in I64 are made by different detector. One that I want to show you here is the so-called micromegas detector, which is a detector based on this principle. You have a gas enclosed within a surface. The gas is usually a mixture of argon and CO2, and you have two cathodes, one at lower voltage, and when the an electron, for example, or any charged particle passes in this region, it is filled with this gas, which is order 5 millimeters, you can have some ionization, and the electron-ion pair travel through this gas up to they reach a second part where they accelerated by a large magnetic field, and they produce an avalanche that basically hits some silicon strips where you can sense the charge, and so you can know where the particle has passed. If you basically use two strips of silicon, two directional strips of silicons, you can reconstruct the impinging position of your particle. This is a picture of what is the detector, and here the result after a long exposure to the beam. You can see the profile of a beam, for example, in this situation. But this is a very broad beam, and you see that the macromega reproduces the shape of it. So after the tracking part, you have the so-called SRD detector, that is the synchrotron radiation detector. So as I said, we need to distinguish between hadrons and electrons, and at this energy, for example, it's impossible to use a Cherenkov detector because all the particles would emit radiation, Cherenkov radiation, basically in the same way, and so we have to rely on something else, and the easiest thing to do is to rely on synchrotron radiation. So since there is a magnet and the electrons are bent to measure their momentum, they emit some synchrotron radiation, which is emitted according to the Larmos formula, depending on the radius of their trajectory, but most of all depending on their gamma to the fourth power. This obviously means that at the same energy, an electron will emit much more synchrotron radiation with respect to an hadron. And then if you detect these photons, you can distinguish between the two kinds of particles. Here you have a profile of a detector, which is basically placed between, here you have the position of the unbent beam, so how the beam should go if there was no magnetic field. Here how the beam passes with a magnetic field, and the photons are emitted along this trajectory. And they hit a detector, which is made by plastic scintillator and LED layers led by photomultipliers, so you can detect this light. And here you have two different spectra. For example, for electron data, also with the comparison with Monte Carlo, you can see it's very good, but also for a data set composed of pions crossing, for a bion beam. You can see that the difference in energy is very large, so that applying a threshold, you can reduce in a very effective way your contaminants up to 10 to the minus 4, 10 to the minus 5 in efficiency. You have some pictures of the detector, how it is made. As I said, there are layers of plastic scintillators and LED, many of them order 100 of these layers. The light emitted by the plastic scintillator is conveyed to the PMTs by these many fibers, and so this is the system basically when it is being mounted. Have all these different layers, one on top of the other, which compose the modules of this detector. Okay, this is mainly the most important upstream detector, and then you arrive basically after some tricky station here. For example, you have micromegas, and micromegas. You arrive to the electromagnetic calorimeter, which is the heart of the experiment, where the like LiDAR matter production, if LiDAR matter exists, occurs, and where you measure basically the missing energy. This is a so-called shashlik calorimeter. Shashlik is a kind of Russian barbecue, where you put your meat and you with some metal rods, and you cook it on fire. And so, since there are some metal rods which hold this cell vehicle, this is the name of the detector. It's basically a series of, again, plastic scintillator and the lead layers, which are then read by these fibers, that inside this module, they are twisted along the center, so that there are no, let's say, dead spot inside the cell. The calorimeter of an A64 is composed from many of these modules. It's 6 by 5 of these modules. And the total length, it is 40 radiation length, but is enough to stop, contain any electromagnetic shower. Here you have, for example, a spectrum of the energy measured by this calorimeter with an impinging positive electron beam of the SPS beam. Here you have a peak of the electron of a primary beam, and you can measure the resolution, which is fair enough for this kind of experiment. And also you can see the contaminant part of the beam. So as I said, there is some fraction of a percent of hadron contaminant. This plot has been performed before any other analysis cut. So here we have both the primary electrons and also the hadron contaminants that they do not deposit all their energy in the vehicle, but they punch through, and therefore you see this shoulder here, and also some very low energy events here. So here, this, if you don't have any other way to react to the event, for you this is, for example, maybe missing energy event, therefore the background event. Okay, now after vehicle we have the last part, which is the downstream part, which is composed by VITO, 2 VITO muon produced inside the vehicle, and a very large hadronic calorimeter. The VITO is a fairly simple detector. We're talking of 3 layers of plastic scintillator that you can see in the photo here. They are fairly thick because they are about 5 centimeters thick, and they are superimposed, so to don't have dead spot. They are read by PMTs, and this detector is placed right after the electromagnetic calorimeter. So the important role of this detector is that one of vetoing all the muons which are produced in vehicle and then escape with a lot of energy. Here you have the very nice Landau peak of the muon resulting from the test of this detector. And with this kind of detector you can reach efficiency in rejection of the muon, such as you have only 1 muon in every 10 to the 4 particles. Finally, this is the HCAL, which is again similar technology, but with rougher segmentation. We are again talking about lead and scintillator, and this time iron, because it's very big and lead costs a lot. And then we have optical fibers to bring the light outside the plastic scintillator, and again a PMT readout. We have 4 modules which are basically 1 meter in length, and the main role of this detector is to stop hadrons, and for example neutral hadrons, because we can have a production of neutron with high energy, or neutral mesons too. And for example here we have the plot of what happens when you have a pion impinging on this detector. This is only one module, so the energy deposited on one module before a normalization, so just the ADC count. And here you can see this peak is when the pion undergoes a hard interaction within the hadronic calorimeter, which results in a hadronic shower that is somehow contained, and so you have a peak at the energy of the pion. But then you have also event where the pion does not undergo any hard interaction in the H-cal, and therefore what happens basically is that it only leaves ionization track, and this is a dangerous event, because if this was, instead of a pion, was a neutron, for example, you wouldn't even have this ionization band. So this is a way to evaluate how many hadrons cross the one module without having their hard interaction and depositing their energy. And since this number is order 10 to the minus 3, you can easily evaluate with 4 of these modules in a row, which is the probability to have such an event, which would be the background, and it is basically 10 to the minus 12. So this is a large enough H-cal for an A64. Okay. Come now to the analysis of an A64, which has been collecting data since some years. And here is a typical so-called hermeticity plot of an A64. So the analysis is done in that way. Where you apply all the cuts that identify, for example, a clean impinging electron track. So, for example, using information of the tracking, you ask for no activity in the veto, and then you do some request regarding the shape of the electromagnetic shower inside the vehicle, which has to be compliant with the typical electromagnetic shower event. And then what remains is this plot here. So the events surviving all the cuts are these. Here you have the energy deposited in the vehicle, and here you have the energy deposited in the H-cal. The signal box for this kind of experiment is an event where you have lost at least half of the initial beam energy, and there is basically no activity inside the H-cal. So what does this thing? These are, for example, neutral hadrons, which are produced in the E-cal, and they, for example, are not detected in the veto, and they arrive to the H-cal, and they deposit some energy in the H-cal. So this is basically an energy conservation band, where some energy was deposited in the E-cal, and some energy was deposited in the H-cal, so the diagonal should be, let's say, from 100 to 100 GeV. It is not to 100 GeV. This is because an A64 has a trigger that requires for an event to be saved to have some missing energy, because otherwise it will save a very large number of events where nothing interesting happens, so just electromagnetic shower of 100 GeV. So you require a threshold of the missing energy at the trigger level that select somehow more interesting events. So what are the main background for this experiment? You have different possibility. So, for example, the production of a pair of muon in the vehicle, which is lost in the H-cal, and you don't see it in the veto, but also being contaminants, that is to say, hadron and like pions and kaons, they may decay, they may misidentified by the upstream part as electron, and then decay as mimicking therefore a signal, but also some lost neutrals that exit the H-cal and so on. But you can see here that all this event all this background result in less than 0.5 event of background, and this is for the last published Na64 data. Here you have an example of so-called sideband fit, which is done to extrapolate one of this kind of background, which is the upstream interaction, that is to say, interaction of the electron within some part of the tracking elements. And so what is done, this part background is evaluated from data, extrapolating an exponential distribution towards the signal box. So an important standard model process for the calibration and of an A64 experiment is the so-called immune production. So from the point of view of the kinematics, this process, which is the radiation of a pair of muon from an incoming electron, is basically the same than your signal, because instead of from the point of view of the kinematics, obviously. And also from the point of view of the vehicle itself, these events are basically the same to signal events, because muons deposit only a few MEVs inside the vehicle, and therefore you can neglect this energy, and therefore it's like you produce some feebly interacting particle. So you can use this event, you can see accumulated here, for example, to cross-check the simulation, perform studies of the efficiency of the detector for the signal, and so you have a data-driven way between the two states to reduce all the systematics associated to the typical problems of acceptance, efficiency, and Monte Carlo. For example, here you have a comparison between the muon spectrum between data and Monte Carlo, and also for vehicle, and also for vehicle, which the scheme agreement is again quite good. Okay, so this is the result of an A64. The last published result, which are based on a statistics of 10 to the 12 electron on target. The experiment observed no signal, so no events with a missing energy larger than 50 GeV after all the application of the different analysis cut. And this result for the scenario where alpha dark is equal to 0,1 already excludes all the thermal relic for the scalar dark matter particle, but also significant part for the Majorana relic. There is also some very small discovery potential, so we excluded a bit of this part of the pseudo-Dirac fermion relic target, and this is due to the resonant annihilation of positrons. So exactly as what we saw yesterday for the Windamp experiment, is an A64, which has a thick target, and therefore you have an electromagnetic shower inside with many positron and electrons inside. You can produce dark photon via resonant annihilation of secondary positron, and this gives you this enhancement in the sensitivity that can allow to explore deepest region of the parameter space. Actually, I don't have to talk about that, but there are ideas of exploit this effect, varying the energy of the beam, because the position of this peak depends on the energy of the beam, to basically scan the parameter space. But unfortunately, I don't have time to talk about it now. Okay, so this was the part regarding the invisible searches of an A64, but an A64 already did also some searches for visible decay of dark photon, and in particular searching for the X17 particles, so the same X17 that could explain the anomaly for the atomic experiment that was searched for by Padme and so on. So to search for this kind of particle that in the parameter space of interest has this lifetime here, so very short, the setup was slightly changed. The experiment was used not anymore as a missing energy experiment. So we are searching now for a visible decay. So it was introduced a new very small tungsten-based calorimeter, so plastic scintillator and tungsten, and this is the place where the interaction is supposed to happen, and then you can produce a dark photon, your X17, that will decay in electron-positron pair. So after this target here, you have some tracking stations, and then the vehicle itself. So the idea was to see a track here disappearing, and then the decay of electron and positron, and two distinct shower shapes inside the electromagnetic calorimeter. So this was a setup, and the A64 collected some data in 2018, which was enough to exclude the sum of a parameter space of the so-called beryllium anomaly or X17. So the plot you saw yesterday when we were discussing about Padme and that the remaining part of the parameter space that Padme is targeting is here. The exclusion limit on the lower part has been set by an A64. So this is the result. You can see it that has a shape of a typical beam dump experiment, and in this case, an A64 is a simple beam dump experiment. So there were also ideas on how to cover the last remaining part of the parameter space. So why it's the limit stops here is not a matter of statistics, but as for all beam dump, is a matter of lifetime of a particle. The particle is so short-lived that you produce it in your dump, in this case the WCAL, the tungsten calorimeter, and then the electron-positron pair resulting is degraded by the interaction within the dump, therefore you cannot measure the electron-positron in the electromagnetic calorimeter and in the tracking system. So to achieve some sensitivity here, you don't need much more statistic, but you need, first of all, to redesign a bit your apparatus. And the idea in particular is to build a more compact tungsten calorimeter so that you produce your dark photon here, X17. It has enough lifetime to travel this space and decay. Then you apply, you use a vacuum chamber to have your track with magnetic field to divide the tracks and to be able to measure correctly the angle between the electron and positron. And this is a way to overcome the limits of this measurement. So this possibility is being discussed in the collaboration, and probably in the next few years will be adopted to perform a final measurement of this anomaly. Okay, we move now to the parallel effort of an A64 collaboration, A64 collaboration, which is an A64 mu. So exploring the dark sector with a muon beam and not with an electron beam. So why you should use a muon beam instead of an electron beam? The idea is to access to other variations, say to the other matter model, that foresee a very weak coupling to electrons, but instead where you have important coupling to second generation lepton, mu and tau, for example. One of these scenario is the so-called L mu minus L tau scenario. I won't go into detail here, but the reason why it is considered very interesting is because it could be an explanation of the so-called G minus 2 anomaly. So this scenario has raised a lot of interest, and the idea of an A64 collaboration was to perform a new measurement with a muon beam to try to exclude this theory, or maybe discover something. But if you want to do such measurement, you cannot use the same exact technique because muons are penetrating, and you cannot simply measure their energy before and then the energy deposited in the vehicle. You have to measure the momentum with a spectrometer after they interacted in your target, and then you perform, that is to say, a missing momentum experiment and not anymore a missing energy experiment. So the detector setup of an A64 mu is different, even if basically the components are all the same. So you have a first spectrometer, which is composed of tracking station for micromegas, straw tubes, macromegas, straw tubes, a bending magnet, some focusing quadruples, and from this first part here tags the beam of muon and defines the initial momentum of the muon, which by the way is 160 GeV from the beam used by an A64 mu. And then you have downstream part, then you have your target vehicle where you hope the reaction to occur, and it's basically the same thing as the production of a dark photon. We have exception, but now the particle radiating is a muon, not an electron. And then you have another system of magnet and tracking, so another magnetic spectrometer, to measure the momentum of the muon. If the muon has undergone such a reaction, is has lost some momentum, and then you will see the bending due to the loss of momentum in this system. So again, not a very beautiful experiment, another experiment in line. This is another region of a North area, and this is the setup. You can see some tracking elements, magnets here, and the tracking elements, and this is the calorimeter where the reaction is supposed to happen. And this is the parallel of the hermeticity plot that I showed for A64E. Now you don't have E-cal versus H-cal, but you have the final momentum of the muon measured by the spectrometer versus the sum of all the energy deposited in the different E-cal in the E-cal system. In particular, the dominant contribution is the E-cal, which is the target where the reaction is supposed to happen. And here again, the signal box is between 0 and 80 momentum, which means that you accept as an event of signal an event where half the momentum of the muon beam was lost. This is the region where the most muons accumulates, since they simply didn't lost any of their momentum, and this is the energy conservation band where the muon undergoes some hard interaction inside the E-cal or the H-cals, and they deposit their energy, and some of the energy therefore is transferred to the H-cal, and when you measure the momentum, you measure a lower momentum. And it's not working anymore. Okay. Again, even in this case, the plot that we're seeing is obtained after applying many analysis cut, and you pass from the, I can say, first raw sample where you collect all events, then you start to put constraints. For example, the first cut is on the timing of the event, so you want to be sure all the signal from the different elements of the detector are in time. Then you clean your sample, asking for a single ETH per tracker, since if there are many different particles sitting in a tracker, it means that something else has happened. There is a range for the momentum of the impinging particles. Then there is a quality cut on the downstream momentum, and then you want the energy in the E-cal in the VTOLs to be compatible with a MIP, that is to say a muon. And this is the different passes of the analysis. You can see that the spectra of this hermeticity plot cleans at every step, and at the end you are left with clean events, that is to say events where the muon crossed your system. You measure the momentum before, momentum after, and you have no loss of energy. And this again is the signal box. So if you see something here, after you have selected your events, you look into your box, you see something, you expect to have a signal, you call it a signal. This didn't happen in the 2 times 10 to the 12 to the 10 muon target that NA64 mu collected, and this allowed the collaboration to set this very interesting limit on the scenario of the vector-mediated light dark matter, while now it's not anymore a dark photon, which is Z prime, that is to say a particle interacting only to the second generation lepton, in particular with muons. And this result allowed to exclude this one, that is the so-called G-2 band, that is to say that region of a parameter space that could explain the anomaly, the momentum anomaly of the muon, if that was the theory underlying that effect. So this is the result of this experiment, and as a first statistic collected by them, I think is quite good. Okay, but NA64 mu can say something also in the normal dark photon scenario, since obviously if a muon can radiate a Z prime, can also radiate a normal dark photon, and more than that, since the muon are more massive than the electrons, they are the emission of high energy dark photon is favored with respect to an electron beam of the same energy. So if you want to explore, for example, this region of the parameter space with an A64, it's really difficult to do it with electrons because the cross-section goes down, and here you see the projections that are for the electron part are enough to cover to reach almost the last thermal target, but they're not enough to cover this region. You can cover this region with muons, and this is the projection for muons. Obviously, this is a very optimistic statistics because you have to collect a lot of data, but this can be considered the final goal for this such of effort. Okay, we finally come to the last experiment we want to talk about, and this is an experiment that is actually not existing, but will be a future experiment. It has been studied, and preliminary studies are being done, which is the so-called LiDAR matter experiment, or LDMX. You can look at this experiment a bit as the ship experiment of the missing momentum. So the state-of-the-art experiment that could bring this technology to the highest level. And the idea is always the idea of measuring a missing momentum, but is a bit more sophisticated, because you don't measure the missing energy in an electromagnetic calorimeter, but you, again, as in the case of muon of an A64 mu, you measure the momentum of the electron that you're using as a beam first and before a thin target. So the target beam energy that you're thinking to use is between 4 and 8 GeV, and the signal signature is the result of what you can expect from dark matter production via radiative process such as the A-Strahlung. So a low energy electron which lost a significant transverse momentum. So here you have an information which is also directional with respect to the simple missing energy, where you just measure the energy before and after, and no activity in all the other part of the experiment, which are an electromagnetic electronic calorimeter, and electronic calorimeter, where you expect to measure only the low energy electron. So the sketch is basically this. You have a magnetic field between the tracking station before and after the target, so you can measure the momentum of the impinging particle and of the exiting particle, which is always an electron. And so that's the strategy that itself is not really complicated, but it's true that there are very challenging technological things to overcome, and I will discuss about that. So the LDMX experiment will be realized at SLAC, which is Stanford Linear Accelerator Center in California, and this is the host of the linear accelerator of SLAC, which you can see here, but also of what was the PEP-2 collider, where Babar was placed. So we talk about Babar, now you can see where Babar was located. And actually the beam line that links the LINAC, the linear accelerator that we will use by an A64, and the experimental hall, which is this end station A here, does not exist for now. So this is something that has still to be built, but there is a project and already an idea on how to transport the beam to this facility. As you can see here, this is the part that it still does not exist. There are this part here, so this is something that has to be done. And so the facility will allow to provide a very low current beam, so one particle impinging at a time, which is what you want for such an experiment, but with a very high repetition rate of 37 megahertz, which means that you want to perform a missing momentum experiment at this rate. You have basically to measure particles every 27 nanoseconds. So this is really challenging. It's probably the most challenging aspect of of the experiment. So here you have some plots that show the strength of measuring the missing momentum of the electron instead of measuring only the missing energy, because here you have the plots from simulation of the missing momentum, the recoil energy of the electron scattered after the production of a dark matter particle for different masses. And here you have what comes, for example, from regular Bremsstrahlung. So an electron scattered via regular Bremsstrahlung has a distribution. And as you can see, for all the masses, there are important regions of this plot that are in common between the two processes, which means that whatever cut you place on your recoil energy of electrons, of the electron, you will have some background from, for example, a reactive process such as Bremsstrahlung. Obviously, providing that you don't see the photon, but this is just a conservative idea. Otherwise, if you look at the transverse momentum of the electron, you will see that for the regular Bremsstrahlung, this quantity is almost always 0, while instead for dark matter, the momentum distribution has a significant, observable quantity, because obviously dark matter is light but has mass, and so there is a kinematic difference. And if you go down and down with masses, so at the 10 MeV, you can see that this goes in the direction of the background, so you will have less rejection power if you were to come to other effects. But still, this is the proof of how measuring the missing transverse momentum is really something that can give you help in rejecting the background for this experiment. So here you have a sketch of the detector. The scale, as you can see, is not particularly big. We are talking of 4 8 GeV beam energy, so you really have to contain an energy which is not incredibly large. And so you have the first part here, you can see, is the tracking part, where the tracking system are placed together with the target where reaction occurs. This is enclosed in a magnet for the measurement of the momentum.
Luca?
And then you have a system which is to
Hello?
be very...
Hi, Luca. I had a question on the previous plot.
Yeah.
Could you explain a bit more the Bremsstrahlung process of the particles you're working with? Because as far as I understood, it was more something you had into account for the mu1 because of you cannot detect it very easily in the electric colorimeter, so that's why you had sometimes big mu1 detectors, but now you're using it for the electron too, I think. So how what's the process? What are you trying to
So the idea here is that we are talking, I still didn't say it, but their target in thermostatistic is 10 to the 16. So you want to control what's happening in your detector to a very, very precise level, and you want to have no possible weird background entering your signal window. So whatever handle you have to distinguish between LiDAR metal production event and something else which is standard model, you want to use it. So missing energy itself, which for example in X64 use, is an information, so is the information that some energy was lost, but maybe not enough, because you may have some standard model process, very rare for example, that gives you a missing energy without, at the same time, you may think this is dark matter. So here you have the comparison between the recoil energy of an electron, which has, okay. So let's assume that an electron, instead of doing A prime Strahlung, you have a normal Bremsstrahlung, okay? So you have a photon, Bremsstrahlung photon, and your recoil electron, okay? But this is very common process. So in 10 to the 16 electron target will happen many times. Okay, many times. So it may happen for some time, maybe, that you are losing the radiated photon for some reason. You are inefficient in your detector. It's really complicated to control things up to such a very large number of events. So you remain with an electron in your detector, which has been scattered, okay, and it's lost energy because it has produced a photon that you have lost. So here, just relying on the missing energy, you will not able to distinguish between the dark matter and this a weird event, but in 10 to the 16, maybe something can happen. Instead, if you, instead of looking, at the missing energy, basically the energy of a scattered particle when it's bound to the missing energy, but you look at the momentum, you can see that there is a significant difference, because we expect the transverse momentum of a recoiled electron from dark matter to be significantly larger, and for normal Bremsstrahlung, the electron just goes straight. So this is the reason why this helps. It's not the only thing, obviously, but this is just to give you an idea of how. But it's intuitive. You have basically more information. You have a three-dimensional information instead. You miss the momentum instead of missing an energy, which is just only one number. So.
Yeah. Thank you.
Okay, so I was describing the detector. This is, as I said, after the target, you have a calorimeter to measure the energy of the scattered electron. And around the calorimeter, you have a very thick hadron calorimeter, which has the aim to detect, for example, again, as in the A64 case, hadrons or particles that may produce in interaction. You have to understand here that this large number, we have to think of very weird standard model processes where is the result in a background, and I will see some in a second. So I will now talk about the two most interesting detectors, which are the tracking error and the calorimeter. The tracking follows the same technology as what was used by HPS. In fact, these are the same people building the HPS tracking system and this system, and this is based on silicon strips. We have two stations, one before the target and one after the target, which by the way is tungsten, 0.1 radiation length. So the material budget of this detector is very low, and this is good because you don't want any, for example, hard interaction of initial electron happen here, or at least you want to be able to distinguish. So after the target, you have six layers of these trackers, and this allow to reconstruct the momentum of a recoil particle with good efficiency between 50 MeV and 1.2 GeV. So the target is 0.1 radiation length, and this is just a compromise because on one side, if you increase the thickness of the target, you will have potentially more interaction and therefore produce more dark matter events, so a larger yield of produced dark matter. And on the other side, this may result in multiple interaction, degrading the energy and bring into background events, and so this was chosen as a good compromise. The magnetic field, as I said, surrounds both the tracking dedicated to the incoming particle, which is called the so-called trigger tracking, and the recoil part of the tracker, so you can measure the momentum of the particles. Okay, this is instead the vehicle, which is something very different from what we saw in all these experiments we have discussed up to now. So they need something very fast, because as I said, they want to go to up to 27 nanoseconds per particle, and they want something that is really radiation hard, because you are making many particle impinge on your detector. And for this aim, we're thinking of something a bit different from the classical scintillating crystal or plastic scintillator, which is this sampling calorimeter made of silicon and tungsten wafer. So this is a sophisticated detector that behaves a bit like a series of tracking detectors. To say, it measures the number of the flow of particles through each of its plane, and you have many of these planes stacked one on top of the other, and basically for an impinging particle you can basically reconstruct the event with a very, very important precision, and this is a very, as I said, very fast detector. So and this is fast, it has to be fast also because vehicle will be part of the trigger of experiment. So you have to trigger 27 nanoseconds and you need something fast. So this is something quite top-notch and state-of-the-art regarding what you can do with this kind of measurement. Okay, here you have the summary of some studies that have been performed by the collaboration to try to see to study what are the dangerous background of such an experiment. So you are going up to the 10 to the 16 level, that is to say you are making your 10 to the 16 particle impinge on the detector, and so you have for sure you will have some very common event, so production of Bremsstrahlung, Trident, and so on. But also, the down you go, up you go in statistic, you see things more and more strange, and processes of a standard model which are also less studied. So we tried to make a list of all these processes. I won't go into detail here of everything, but they thought also for each of these background which are the handles that they can use to reject them. So you have many possibilities are shown here, and depending on the kind of event, they think they hope to be able to arrive at a zero background measurement. They stop at 10 to the 16 also because they expect neutrino processes at point are irreducible, where you produce neutrino and you have no way to distinguish from so again another neutrino floor for accelerator experiment. So you can see that 10 to 16 is enough to have a reasonable reach for this experiment. This is a simulation, obviously, and shows what is the projected sensitivity for this experiment in a first phase and in a second phase, which changes depending on the statistics. So first one is a bit more achievable, it's 10 to the 14, and you have some differences depending of the kind of beam you were going to use. And then you have the phase 2, the upper limit to the upper limit, that is to say 10 to the 16 electron target, that corresponds also to many years of taking data. So very challenging and but also very good result. Here there was some different curves that represent the variation in efficiency depending for example, the discovery of some background events. So if they were not to be able to run the experiment at a zero level background, for example, they will have 5 of 10 events of background. This is how the upper limit will change. So you can see it will still be very good. So since this is my last talk, I just want to wrap up things a bit and to discuss. To summarize what we have discussed in these four lectures. So I convinced you that vector-mediated light dark matter is an interesting model to explore, since it gives rise to a very rich phenomenology, which foresees particles which are very long-lived, very short-lived, that can decay to particles of a standard model, that can decay invisibly, and this has brought to many different experimental approaches to explore these scenarios. And we saw searches at colliders that, for example, in a visible scenario, comes from the up of a parameter space, but also has some possibility to perform some displaced vertex searches. The same for thin target, and we also saw beam dumps, which have this shape due to the fact that they are limited not by the coupling itself in terms of number of particles produced, but by the fact that the particle decay inside the beam dump itself that cannot be measured. So this is for the visible. For the invisible, with the same, we saw the case of Babar, and for now, one of the most, or I say the most important limits set by NA64 in this invisible scenario. So this is the status now, but there will be many new things coming in the future. First of all, SHIP, LDMX, that we probably explore very intensely this parameter space. So who knows? Next year we may have some good news. Let's hope for it. And with this, I conclude. Thanks to you for the attention, and I'm open to questions.
Questions? Okay.
So I have one very simple question. So when you mentioned the production and detection of dark matter, then you had the epsilon square.
Yeah.
And then when you say that we go to missing energy, my understanding was that you have just epsilon because you have to produce it, but there was an epsilon square, so I got a bit puzzled.
No, we have epsilon square and epsilon square.
Yeah.
Yeah, let me. So here is epsilon square here and epsilon square here. So epsilon to the fourth.
Epsilon the fourth. Okay, great, thanks.
So that's the reason why you need to take. Okay.
Thanks.
Yeah, and back to your final slide. Sorry, just skip around.
Okay, no problem.
But yeah, so in the summary plot on the visible dark matter, yeah, so you have like all these beam dumps on the bottom left, which are basically limited by the lifetime of the particle. Yes. And then you have like a bunch of CMS collider type experiments like high mass. What do you think is the best strategy for covering that red band? Is it somehow like collider CMS style experiments, or somehow higher energy beam dumps?
Yeah, I think that you have to weigh. Maybe the most promising one is the displaced vertex, and this can be done both at Accelerator and at fixed targets. Unfortunately, it's not here, but maybe remember the projected sensitivity for HPS, which is a very small thin target experiment, which is here, so it has some discovery potential.
Yeah, so you can cover a lot of that parameter space, from just like reanalysis of current detectors, or would you need more detectors?
I think you need to go on with also the collider. I expect some changes to be done, because often what happens is that the searches from collider are limited by triggers, because they were not thought to search for this kind of particles. So basically you lose your efficiency due to the fact that you did not save that event. And so I expect for ILUMI, for example, to have interesting news from the point of view. So I think in any case, a different strategy is the good answer, so the right answer.
Yeah, okay, perfect, thanks.
Okay, so since this was Luca's last talk at our school, thank you very much, Luca, for accepting our invitation and for providing us with this great set of talks on light dark matter. So please, everyone, a warm round of applause to Luca.
Thanks.
And it's time for a coffee break. We'll be back at 11:30. So let's go with our last talk today by Javier on dark matter detection. So please, Javier, go ahead.
Okay, well, good morning. So today we're going to have our fourth lecture. So remember that last time we talked about cryogenic crystals. This time we are going to focus on semiconductors. That you can see that semiconductors can be used to probe many different candidates for dark matter. I'm going to focus on this, but I will be talking a little bit about how it is used for looking for other candidates too. But since we've been talking about the WIMP a lot, now I'm going to change a little bit the targets. Instead of using the nuclei, we are going to use the electrons in the materials as targets. Okay. Tomorrow we're going to have our last talk, and the goal is to at least dedicate some of the talk to axions and very light particles, okay? So it would be something in this area, but at the end of this talk also, you are going to have a poll, and please add anything that you would like to hear about that I did not talk about, and I'll do my best, okay? Okay, so we're going to start with a keys, okay? So here, what you are looking at is a spectrum. This is a prediction for light dark matter candidates, okay? Here you have the parameters, so we are using a target mass, a dark matter particle mass of 10 MeV. So this is very light. Remember that on our last talk, we were talking about things in the order of GeV. Okay, so this is MeV, so 100 times lighter. And this thing interacts with electrons, and it has a light mediator. That's what this thing means here. Okay, so we are assuming these two things for producing this plot here. What is in the horizontal axis is the amount of charge that it produces, okay, and in a silicon target. So you have a silicon target, you have dark matter coming from the halo. When it interacts with that piece of silicon, it will produce some ionization, and the spectrum of the ionization that you expect to see from the dark matter velocity distribution in the halo is this, okay? And this is just the normalized rate. So by looking at this, please think about this question here. I'm gonna, when I change the slide, I'm gonna go into the poll so you can vote, you can join and vote, okay? But I won't be able to show you this thing together with the voting system because to do that I have to pay, okay? So again, think about this. What is better? What would you prefer to have? A mass of 1 gram, so a very small detector, and a threshold of 1 electron? A mass of 10 grams, but a threshold of 3 electrons? Or 1 ton of ultra pure silicon and a threshold of 8 electrons? So look at this, make your decision, and I'm going to change the slide, and please join and vote, okay? So, is this working? Well, one person. This is very slow. Well, you practice, there's going to be more polls, so be sharp next time. Okay, 20 votes in. Oh, I thought it was going to show live this time. Well, okay, now we have an amazing turnout of almost 30. We get to 30, we move to the next slide, and we know the answer, okay? Oh, good. Okay, so, wrong. Okay, so, here, well, most of the people voted 10 grams and a threshold of 3 electrons. 1 gram is the right answer in this case, although these things are close, and you definitely don't want this. Let's see why, okay? So, again, let's take a look at this plot. The mass of 1 gram and 1 electron will give you a rate in these normalized units of 1, okay, whatever. Then a mass of 10 and a threshold of 3, so 3 is here, that is something smaller than 0.01, okay? So 10 times this is still going to be less than 1, okay? So you are, so far, 1 and 1 electron is winning. And a mass of a ton is 10 to the 6, but this is smaller, it's sometimes 10 to the 7, so you are still less than 1, okay? So what's the take-home message? That in the light dark matter land, threshold is the ruler, okay? You really want to have as low threshold as possible. And this is going to set everything for our decisions on what targets we want to have and what kind of detectors we want to have. So this is very shocking. You prefer to have a 1 gram detector compared to a ton that is 10 to the 6 times larger, okay? So this is a lot. Still, with a very tiny tabletop detector, you have a better sensitivity than a huge 1-ton experiment, okay? So be aware of that. So which is going to be our detector of choice for this? Our detector of choice for all the talk today is going to be CCDs and CCD-related detectors. So you may have heard about CCDs. CCDs are what used to be in digital cameras. Okay, so these are pixelated detectors. This here is just a piece of silicon, in this case, okay, with pixels. And if we look at one pixel, what you may have is that you have some ionizing radiation that goes through this silicon, and it produces some electron-hole pairs, and because you have a potential difference here, these things will drift, and you will be able to measure these things. I will tell you how in a few slides. So when I'm talking about ionizing radiation, well, you typically think about muons, alpha, beta particles, gammas, but photons, I mean, in the optic range are also ionizing radiation if you are silicon. Okay, so if you are made of silicon, photons will come in and will produce a pair of electron holes because the band gap of silicon is only 1.1 eV. So that's why CCDs were used as imaging sensors, and they are still used in super sensitive experiments. But in your cell phones, now there is a technology that is pretty close to this, is the one that you are using in Anna's lab, that is CMOS, that work essentially the same, but with some important difference that we can talk about at the end. So this was the origin of the CCDs. So this is how you can use them as detectors for particles. And now we're going to discuss a little bit how can you use these things to look for neutrinos or WIMPs, okay? So you have the silicon lattice, this thing is a crystal, and then you have a particle that is neutral, okay, a neutrino or a WIMP. It interacts with one of the nuclei in the same way that we've been discussing so far. It produces a nuclear recoil, and that in turn produces ionization if enough energy is transferred, okay? And I'm not going to discuss a lot more about this. This will be Dario's talk tomorrow, okay? But what I am going to focus on is this case in which you have a dark matter particle or an exotic new particle, okay? And it interacts with one of the electrons in the valence band here, and it transfers enough energy to this thing so it goes into the conduction band. And when that happens, you create an electron-hole pair, and then hopefully you will be able to see this signal, okay? And remember the plot that I showed you at the beginning. You really want to have a threshold as low as possible, so you want to have something that is able to see, ideally, single electrons. So how are we going to get there? This thing here is a cartoon representation of a CCD detector, okay? So we are looking at this from the top. All these structures here are printed on top of a piece of very thin silicon, okay? So you have a silicon wafer, and on top of that, you have these structures here. The way then a CCD works is that these structures are conductive structures, okay, that are placed on top of this piece of silicon, and then you can apply voltages to these things. So you can apply different voltages. So for example, like what we have here, if you set P1 and P3 to a high voltage and P2 to a low voltage, then you will have here a potential well, okay, where you can accumulate charge in there, sitting in this potential well. Then you have these other structures that are called the channel stops, that these are permanent potential barriers. So you implant ions in the silicon, and that creates a barrier. Essentially, you create a potential wall here. So whatever ionization that you get in the silicon bulk, in the piece of silicon that you have coming from external radiation, it will create charge that will go up, remember, from our previous slide, and then will be sitting on these potential wells. So they will be sitting there, and you don't have any way of reading it. You don't know how much charge is there. So you can expose your detector for minutes, hours, even days, okay, and accumulate charge in these potential wells that we are calling pixels, okay? And the charge will sit there for as long as you want. And this is also truly amazing, that you can have just a few electrons sitting in a potential well for days, and nothing bad happens to them. They don't go bad, okay? So it's true that this is cold, but yeah, okay. So the way to read out this thing is the following, because as I told you before, you don't have any readout structures connected to this thing. But you can control these potentials, okay? So you can change those. And that's exactly the game we're going to play. So what we are going to do first here is to, let's say, lower P1 and keep P2 low. So now the charge that was in the potential well here is distributed between these two phases, okay? And then we move P2 up, and now you have some magic happening. The charge move 1/3 of a pixel, okay? And if you keep doing this after 7 steps, using this as a wave, okay, you are moving the charge from one position to the next. And the charge that was sitting here, it's moved into this other structure that it's at the end of the active area of the CCD, okay, that this thing is called the serial register. This region is also part of the same piece of silicon, okay? The difference between this region and this is that the channel stops that prevented the charge from moving in these directions do not extend into this area, okay? So now charge can move freely in this direction. And these other structures here are exactly the same as this, but you can control them independently from the parallel clocks here, the parallel structures there. So you can play the same game here and move then the pixels or the charge of each of the pixels one by one into the readout structure that is here, okay? So this last step is what allows you to actually measure how much charge was in a pixel, okay? So this design, it's very nice in several senses. In the most important one is that in principle you can have an arbitrarily large detector for this. It can be huge, and still the capacitance of the output, okay, the sensitivity of the output is just set by the size of this structure here in the readout stage. The problem with this, what's the problem with this? Can you think about what may be the problem with this? Is that this is very slow, okay? You read the pixels one by one, and typically you will have millions of pixels here. So you are shifting the charge and reading the pixels one by one. But at the end of that, you have a very nice measurement of each of these things, and if you are not that worried about timing, then you are good. And with dark matter, in direct detection searches, we are not worried about timing, mostly. So here, I told you that you move these things into a readout structure. So what's this readout structure? So now these H structures that I'm showing you here, they are the same as this. So we are moving the charge in this direction, okay, using this wave movement technique. So then at the end of that, you have this thing here that is the part of the CCD that allows you to measure how much charge was in the pixel. How you do that? So, well, you move the charge from this last horizontal or serial clock, and then you move it here into what it's called the summing well. So after that, you forget about whatever you had before, and you only worry about what we had here. So you have the charge sitting here in a potential well that we are calling the summing well. Okay, then you have a potential barrier, that is the output gate, and then here you have something that we are calling the sense node, that is the only thing in the CCD that is connected to a measuring device. All the other stuff is just control signals, okay? This thing here is coupled with through a capacitor with a voltmeter, essentially, okay? And here I'm showing you the measurement that we are doing, okay? So we are measuring what's the voltage of this thing when there is no charge in it, and we are sure that there is no charge in it because we have this switch here that we can connect, and this goes to a very, very negative voltage, so it takes out any charge that may be there. But then we open it, and now this thing is floating, okay? So the voltage in this thing is just set by all the voltage in the surrounding environment, okay? And it's very hard to calculate what's that voltage going to be, so we measured it. What's the voltage of this thing when this is empty? Okay? Is this value, okay? The longer you measure, in principle, the better your estimation of what's this level it's going to be, okay? Until some point. Then we move this thing up using just a structure that is the same as the other clocks that I showed you before, and then the charge wants to go into this potential well that is in the sense node, okay? So after that, you move everything back to the position it was before, okay, and measure again. And now, because this capacitor has some charge in it, the voltage has changed. So you are able to look at this difference, and the difference between these two levels is going to give you a measurement of how much charge you put into this sense node, this capacitor, okay? And then you can move it back, okay? So you have here another structure that you can move up and move these things into the summing well again, and then you start again with an empty pixel. And you can do this as many times as you want. This is the skipper CCD. The standard CCD would end up here. After this, in a standard CCD, you close this switch, get rid of all the charge, and get ready to read the next pixel, okay? But in a skipper CCD, you can do better than that. You can move this charge back into the summing well again, and then you can do this game again and take multiple non-destructive samples of the same charge package, okay? And that's going to be critical for improving our threshold, energy threshold, as you will see. Okay, so just to summarize, here we measure the sense node voltage when there is no charge in it, and all the fields around this sense node are in a given configuration. Then we move the charge into this thing and put all the other fields in exactly the same configuration. And from the change in voltage due to the charge in this capacitor, we get our signal. Okay, this is called the correlated double sampling technique. It's the reason for that is that, well, we are trying to measure the baseline noise, or what's the baseline between two different configurations that are very close in time. So when we subtract it, we can get rid of any fluctuations that change in time slowly or environmental effects, okay? And this works really well, but it has a limit that comes from the fact that there is, sorry, okay, I'm going, yes, sorry. So this works really well, but hits a limit that comes from the fact that everything, all the electronics that we know how to build, okay, are affected by what is called the 1/f noise, okay? This noise is something that produces a very slow change in the baseline of all the transistors that humanity knows how to build. And this is unavoidable. So if you start integrating for longer periods of time to get a better estimation of these levels, okay, then at some point you get rid of all the high frequency variations here because you average them out, okay, and that's nice, but you are starting to be hit by these low frequency changes that change the baseline of where that voltage lives. And this is something that nobody knows how to fix. This is the 1/f noise. But there is a trick that we can play here if we use the skipper CCD, that is this device that allows you to move the charge back and forth and measure it many, many times. And this trick is that if instead of just getting a very long integration to estimate the pedestal and the signal, if we do take many samples that are measuring the same, but in a shorter integration time, then, well, overall, you have the same power to get rid of the high frequency noise, okay? Because you are averaging all of these things. But at the same time, you are not hit as hard by the low frequency noise. And I mean, you can say, okay, but if you have a noise that hits exactly this frequency, and I will tell you, yes, if you have a noise that hits exactly that frequency, that would be really bad. But the good thing about the skipper CCD is that you don't need to read at that frequency. You can just pick a different frequency where you don't have noise, and then do your measurement there. So the skipper CCD allows you to pick where you want to fight your noise battle. The other one, you are just forced to go to low frequency and you will lose, okay? So now the second interactive part of this talk. So this here is data from a real CCD, okay? So remember that as I told you before, this is a pixelated detector, and because you know the order in which you read each pixel, you know exactly how much charge was in each of these pixels, and then you can just put them in an array like this, okay, a matrix, and this will be an image. And you know how much charge is in each of these things. So this was taken at surface level with one of our CCDs, okay, and you get a lot of hits or tracks or signals from environmental radiation, okay? So here I'm showing you 3 different mystery hits, okay? 3 different mystery particles, and please take a look at them. Think about what they can be, okay, from the environment. So we have cosmic rays and natural radioactivity from materials around us. Think about what they can be, and remember that I'm going to change the slide, okay, and then you pick, okay? So, ready? Let's go. Remember, number 1 was kind of a wavy worm, number 2 was a straight line, and number 3 was like a dot, okay? Yeah, when I rehearsed this, the things were moving as people voted, but I don't know why that's not working now. So, come on, we can get to 30 again. 30 votes. Getting close. So again, remember, the number 1 was a wavy worm, number 2 was a straight line, number 3 was a dot. Almost there. Come on, one last push. Oh, there. Good. Ah, perfect. So that's amazing. So it looks like the labs with Anna are working. Okay? So really nice. So yeah, we have electrons, muons, and these point-like thingies that are X-rays or other stuff, but most likely X-rays. So now, oops, sorry. So we have an image. This is just a section of a CCD, okay? We can have this, I mean, the full image is actually many times this thing, okay? And let's take a look at this empty or dark pixels, okay? Because here with this scale, we are not really able to know how much charge is in there, but we can take those and make a histogram. And, oh, sorry, I forgot that this was coming. So this is how a CCD looks like, okay? So you have here, this is the sensor. This is just a piece of silicon, okay? This part here where you see like a line and that it's different from the others in color, this is where all the readout structures are printed, okay? The ones that I told you before. And then these things on the edges are wire bonds that connect those structures to, these are essentially flat cables that go to our readout electronics, okay? So these hair-like cables are, for example, the ones that I mentioned at the end of yesterday's talk, where the other detectors were hanging from these hair-like cables. So these are those, okay? So this is how a CCD looks like. And the idea for the skipper CCD was proposed in 1990, so a long, long time ago, okay, over 30 years, but it took us about 30 years to get it working properly. And this happened in 2017, so fairly recently, about 5 or 6 years ago. The device was devised by Steve Holland at LBLL. This is Berkeley Laboratory in the Microsystems Labs, whom we've been working together with for many, many years. And then we did all the integration at Fermilab and learned how to use these things because these things had not really existed before. So that took a lot of effort. But again, so this is how a full system looks like. This is a system that we have at the University of Buenos Aires, the Lambda laboratory. So you can see that this is fairly compact compared to other technologies because you don't need to go as cold. It operates well above liquid nitrogen temperatures, which makes your life a lot easier. Liquid nitrogen is about 70 Kelvin, so you can cool this down, and you even need to heat it up to get to 140, okay? You need to, because these things are cold, you need to isolate them from the environment just with a vacuum vessel, the same as a thermos, okay? And this is our control and readout electronics. So you see that these systems can be very, very, very compact. And I mentioned that it operates at 140 Kelvin, that is around 130 below zero, okay, Celsius. And do you know, I mean, can you guess why? So the reason is that we want to minimize the thermal fluctuations, okay? So we minimize the dark currents, the electrons that are promoted to the conduction band just by fluctuations. But because here the band gap is not milli-eV, just eV, if we have a very good quality crystal, we don't really need to go below this because the thermal fluctuations are already very unlikely to make an electron jump 1.1 eVs into the conduction band, okay? But in the case of the phonon detectors that we were discussing yesterday, the band gap or band gap equivalent is milli-eV. So there you really need to be at millikelvin temperature, okay? So this here is data, again, real data. And here what we are doing is, maybe I'll show this in the other way around. So here, what I'm showing you is what I mentioned before. We take those empty pixels, okay, and make a histogram of how much charge is in them, okay? So this is how it looks. So in the horizontal axis is the amount of charge, and here is the amount of pixels that have that charge. Okay? So this peak here is all the pixels that have 0 charge in them. This peak here is all the pixels that have 1 electron in them, 2 electrons, and then all the other are empty. Okay? So the width of this distribution, okay, it's very narrow. It's 0.06 electrons RMS. Okay? And what does this mean? This means that if you measure this value, let's say value of 0, you are more than 5 sigma away from confusing this with the next charge quantum. Okay? So if you measure 0, the likelihood that you will confuse whatever you measure with 1, it's more than 5 sigma away. Okay? So essentially, when you are running like this, you are running in an electron or particle counting regime in which you don't gain anything by improving the noise because of the quantization of charge. Okay? This gap is there because the electrons and charge are quantized. If you had particles with a fractional charge, they could appear in this valley, but so far we haven't seen any. Okay? So going back to this plot. So this plot is just showing you in the vertical axis what is the width of this empty pixels distribution. Okay? In the histogram that we saw, it was 0.6, but that was after taking 4,000 samples. So you can do this trick of moving the chuck back and forth many, many times. In that case, we did that 4,000 samples, then we averaged those and obtained that distribution that I showed you before. So in the x-axis, we have two things. First is the number of samples that we take. So this one here is just taking one sample as a standard CCD, and then the noise, it's about 3 electrons RMS. So that's the width of the empty pixel distribution. So you will not be able to see, discriminate between 1 and 2 electrons if you have a width of several electrons. Okay? But you start increasing the amount of samples that you take, and you get here to 0.06 electrons RMS. That is what I showed you before, the distribution that I showed you before. And the dots here are actual measurements, and the red line here is just, it's not a fit. It's just taking the value for the single sample readout noise, in this case 3 point something, okay, and dividing that by the square root of the number of samples that you take. That is the theoretical prediction for uncorrelated independent samples, okay? And what you see is that this follows pretty much that prediction, that is the optimal, until here where you start to have some deviation. But this means that we are at the theoretical limit of what these things can do. You cannot do better than this. There is nothing to gain by using fancy techniques of data processing, okay? And the other thing that it's unique, as far as I know, to these detectors is that this resolution is independent of the amount of charge that you have in the pixel. So in the plot before, here I showed you these peaks for a very low amount of charge, 0, 1, and so on. But you can also look at, for example, this is the spectrum produced by a nuclear, by a radioactive source that is called iron 55. The shape of this is not important for what I want to say, but just look at the axis. Here we have thousands of electrons in the pixel, okay? And then if we zoom in into this very tiny region, this is what we see, okay? So we are able to tell apart if we have 1554 from 1555, which is absolutely amazing, okay? Not super useful as far as I know, but still it's cool, okay? And now I'm going to show you how that looks like in an image. This, again, all I've been showing you, it's actual data. This is also, we are taking a very tiny piece of the full image that I showed you before, okay? This square here. And this here is the distribution for the charge in the pixels in the full image. And here we are starting operating this as a standard CCD that can only take one sample, okay? And then we are start adding more samples and looking at how it looks like, okay? So you see here the number of samples, the noise going down, the distribution getting narrower, 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 narrower. Most of the pixels are empty, okay? And now you see here that in this region of the CCD, actually the central pixel had one electron sitting in this pixel, but of course we weren't able to see it until we did the skipper trick and reduced the noise to sub-electron level, and now there is absolutely no doubt that there is an electron sitting in this central pixel, okay? Now that we have found a detector that has an extremely low energy threshold, okay, now we need to find a good place to take it and look for dark matter, okay? So the place is Snowlab. Snowlab is an underground laboratory that is in Canada, in Sudbury, that is inside an active mining operation. So to get there, you have to go down a drift that inside a steel cage that is the same cage that is used to take the rocks out, okay? And this thing goes down at 50 kilometers per hour, that it's very fast, okay? And then this goes down 2 kilometers. After that, when you get there, this is the cage getting to the lowest level, then you have to walk about 1.5 kilometers through an active mining operation here until you get to the laboratory Snowlab that is actually an absolutely amazing facility that is a clean room inside an active mine, 2 kilometers underground. So this is insane. All of the areas inside Snowlab are clean room level, so you don't have any contamination. They filter everything. Once you get there, you feel like it's a normal place. Well, actually, much cleaner than any normal place, okay? And you get there after walking through mud, rocks, and other stuff. So that's amazing. So I will not spend a lot of time talking about Snowlab, but ask Anna about Snowlab, and it's an amazing place. And many, many experiments are here. For example, DEEP, that we discussed in our second talk, the liquid argon experiment, the single phase, is at Snowlab, and also Sensei, that is the experiment that I will be talking about now. So Sensei is the first experiment using the skipper CCD technology to look for dark matter, or actually to do anything, okay? So how does Sensei at Snowlab look like? So here, these are our CCDs, are bigger than the ones that I showed you before, okay, to have more target material. This orange thingy here is just the flex cable to get the signals in and out. And as usual, this thing is inside a clean copper box, okay? So then this thing goes into another bigger box where you have a stack of these modules, okay? Many of these. This box is cooled down to about 130 Kelvin, okay? And we close it and have vacuum inside this volume here, okay? And then after that, we put a copper shield, and we cover that with a bigger copper shield, and we cover that with a bigger lead shield, and after that, we cover that with some polyethylene boxes that are filled with water. So this is to shield us from the neutrons in the environment. This is to shield us from the gammas in the environment. This is to shield us from any radioactive contamination in the lead, okay? So we've been deploying Sensei in many different iterations, and I'm going to show you a little bit how the data looks like for the first run that we had there. So just to get an idea of how important it is to go to Snowlab or to go to an underground laboratory, here I'm showing you, this is a just a section of an image taken at the surface level for 1 hour. So you see that it's full of stuff, okay? This one here is the same, actually not the same. This is 20 times longer than this. I cannot use the same thing because here you would see just a black square, or if I do the other thing, here you will see something that is completely white, okay? So this is 20 times longer at SnowLab, and this is what you have. And actually, I had to pick a section where I had something in there. Most of them are empty even after 20 hours. Okay, so that's how important it is to go underground. So we did a search with Sensei. We took data for some time, okay? And then we did a search. We looked for these low energy events. Remember that we are looking for super low threshold because that's the only chance that we have to see something if we are looking for light dark matter. And after that, we got not a spectrum, but a table, okay? So here, I'm showing you the amount of events that we had with 2 electrons in them, the amount of events that we had with 3, and the amount of events that we have with 4 or more events, okay? Sorry, 4 or more electrons in them, okay? So here, well, we don't have any. We have a completely clean spectrum for any pixels or events or clusters with 4 or more electrons in them. We only have 2 with 3 electrons, and we have about 30 for 2 electrons. So this allows us to set limits to about what dark matter can be or cannot be. So remember this. Again, we are going to be dominated by the lowest energy beams in which we have relatively controlled signal. I'm not showing here the 1 electron events because I'm going to discuss those further on later on this talk, okay? But there we have a much larger number, and that makes that channel not competitive for looking for dark matter. And we knew this beforehand, okay? So now, I've been showing you so far only WIMPs, and yesterday there were questions about other options. In this case, I'm not going to talk to you about WIMPs anymore. I'm just going to show you other options that are benchmark options that the dark matter community have selected as good candidates for comparing experiments, essentially, okay? So on this plot, this is very similar to what you have in a WIMP exclusion plot. In the horizontal axis, we have the mass of the dark matter candidate, okay? And here, the scale, the units are MeV, not GeV. So this is much lower, okay? And on the vertical axis is, again, the size of the cross-section, okay? But now it's the cross-section between dark matter and electrons, not nuclei, okay? Because we are looking for dark matter that interacts with electrons. And what we have here, this line here is the result from Sensei at SnowLab. All these areas are excluded. That is telling us that if we are thinking about a dark matter candidate of 10 MeV mass and a cross-section of 10 to the 35, that is excluded. That cannot be, or bigger than that cannot be, because if the cross-section was larger than that, we would have seen more events than what we saw, okay? So this is the exclusion plot. This is the result from Sensei, okay? And then this band here is what we call the freeze-in line. That is a line that is highly motivated for theoretical reasons, that the candidates that live here have some properties that would explain the long-term evolution of the universe, the large-scale evolution of the universe. So we are really aiming to get here, okay? We really want to be able to explore these candidates here. We haven't so far. This thing here is, if you consider something that is a little bit of different from vanilla direct detection, but that it's very reasonable. And if here what you are saying is, okay, if dark matter can interact with electrons, well, it can interact with the electrons in the sun, okay? And the sun is very hot. The electrons there move very quickly. So then the end effect is that you will have is that the sun kind of heats up, okay, the local dark matter halo and increases its kinetic energy, okay? So you are able to then access some of the dark matter candidates that are much lighter, that would not give you a signal that you can see, because these would be the ones that are boosted, okay? So there is some modeling here, but it's pretty straightforward, because if you are assuming that you can see the dark matter candidate in your detector, well, you can also, it can also interact with the sun, okay? And just for completitude here, it's the form factor. What this means is what's essentially the mass of the mediator. So in this situation, we are thinking about something, the dark matter candidate, that can interact with electrons, and the mediator is light. Okay, that's what this thing means here. That's the only two assumptions that we are making. Okay, but we can go to the other extreme case in which, again, it's dark matter that can interact with electrons, but now you assume that the mediator is heavy. Okay, so remember that for accelerator searches, if we have a light mediator, it's very, very hard in an accelerator. With a relatively heavier mediator, it's easier. It is too heavy, it's hard again. But here you see that the limits from Sensei, although they are the best at some positions, they are now competing with other stuff, like Xenon 110 S2 only. This is in dashed line because this is these are predictions at this point, but still you are now comparing and being competitive with things that have a larger mass. But yeah, so just to also answer the question yesterday, the community has been moving away from only WIMP signals and looking for other options. And another very, very interesting option is yes?
Thank you. In the previous plot, do you know what these benchmark models for the heavy mediator are?
This one here?
Yes.
So this, I mean, this blob actually includes a lot of stuff. I mean, it's not as well motivated as this one, but I mean, we can discuss this afterwards, but it includes a lot of stuff. You can also see that there are two different shades of orange, so there are lots of things there. But essentially, these include families of models that best explain the cosmological observations. So, I mean, you can have the dark matter candidate that solves other problems that you have in cosmology, or you can have a dark matter candidate that just solves one. The ones that live here solve many of the problems. The ones outside maybe just solve one.
Great.
Okay.
Thank you.
So this one here is, oh, sorry, one thing that I forgot to mention here is that in these two cases, we are looking at what is called scattering. So this is very similar to what we had with WIMPs and nuclei. So we have the interaction of two things, and then the same two things come out. Okay, you just have some energy transfer between them. But there is another option, that is absorption. That is essentially that you have a dark matter candidate that can be fully absorbed kinematically in your detector, and then you have access to the full mass of this thing. This is very similar to what you have with photoabsorption and photons, okay, in which the full energy of the X-ray, for example, goes into the detector, okay? This is equivalent to photoabsorption. And if you are in that situation looking for those candidates, also here, Sensei is the most sensitive experiment for a large range of possible masses, okay? At the lowest bound is just the silicon band gap. There, if you have a photon or a dark photon that has a mass smaller than 1.1 eV, even if its full mass converts into energy in your detector, it won't be enough to promote one electron in the valence band into the conduction band. Okay, so this is just to show you 3 different models that are chosen. These are benchmark models chosen by the community that are highly motivated and then that are extending beyond the WIMP paradigm. Okay, so Sensei has been going on since the first skipper worked. Now we are here, okay? We recently deployed more CCDs in a better box, and now we are in our second science run. So the second science run in which we are on right now, we split this in early science run, in which we dedicated all our efforts on measuring and improving the dark count rate, and then a second part of the run in which we accumulate a big corpus of data in order to do a WIMP search, sorry, not a WIMP search, a dark matter search, as I showed you before, okay, but with more mass and hopefully better and cleaner detectors. So regarding the dark counts, one thing that we found out is that a big contribution of the single electron events that we have in the CCD that we cannot get below of was coming from essentially light leaks, but not regular light leaks, but essentially, well, these things, although they are inside a cold box, this box is not completely light tight, okay? We did our best, but it's very, very hard to make things light tight, okay? Anybody in the hotel knows that, because you cannot really close that. So the thing is that although there is no environmental light going inside our vessel, because we have these layers of shielding, the vacuum vessel and stuff, well, the walls of our vacuum vessel are at room temperature, okay? And that's a black body, and that produces black body radiation. So you will have some amount of light inside your vessel, even if it is light tight, okay? So the black body radiation from the walls, then the tail of this thing will be infrared photons that can be seen by our detectors. Those bounce around inside the vessel, and some of them get to our copper modules that, although are closed, there are very tiny gaps on the edges and here in our original design, from which these infrared photons could go into this thing and hit our sensors that are inside these copper boxes. So this here is how the dark count rate looked like in our sensors in this situation, where light could go from essentially everywhere, okay? Then we improved on that by really closing all these gaps, okay? And it went from this to this. These are completely comparable in exposure time, okay? So by doing just this tiny change, we extended the science reach of our experiment by a lot. And this produced the world record for dark counts, that is 1.4 10 to the minus 5 electrons per pixel per day. This translates to essentially that if you are looking at a single pixel, you would need to wait more than 200 years in order to see one electron in that thing, that it's not produced by environmental radiation, okay? And ask Anna, that she was leading this analysis and effort for Sensei, okay? So this is by far the lowest dark count rate of not only silicon or semiconductor detectors, but any kind of photon detector, okay? So, which is also very nice if you are thinking of different or other applications in low rate imaging. So, it's not very clear, but what that does, I mean, what does this mean for our science reach? So I'm going back to the plot that I showed you before. This is the absorption of the dark photon, okay? Was there a question? Sorry. No. This is the absorption of the dark photon. So the previous result is this line, and it goes here. I don't know if you can see it, but if not, follow the pointer. And all this additional region is coming just from the fact that we are able to measure this low dark count rate. Okay, so by using some copper tape, you increase your science reach. Okay. So I've been talking to you about how amazing these things are, but these detectors do have challenges, have problems. Here I'm showing you 3 of the bigger challenges that we are dealing with right now. This thing here is what we call the spurious charge, and it comes from the fact that when you are moving the control voltages to produce this wave-like thingy to move your charge around, there is some probability of transferring some of that energy to electrons and promoting them. And then you create something out of nothing, and that's very unfortunate. Okay, so this is equivalent to dark counts, but when you are moving your control signals. Then there is another thing that is, well, we have this voltmeter or amplifier in the CCD, okay, and there is some current flowing through this transistor here. And any current that you have will produce heat at some level, and that will produce in turn infrared photons. So those photons are another source of light, very, very dim source of light, but it still is there, that is hitting your active pixels and your serial register and producing charge that is not related to environmental radiation. And then, again, we have this thing that is what we call the intrinsic dark current, that, well, you have some thermal fluctuations and the probability of promoting one electron to the next one. And although I told you that operating these things at 130 Kelvin it's enough, that is true if you have a perfectly regular crystal, but if you have a crystal with impurities or dislocations or cracks or whatever, you will create additional intermediate levels that may allow these things to jump up. So we are also working on improving that. Okay? And just, this is my last slide. This is what's coming next. This is the future. So far, the only results that have been published for skipper CCDs have been coming from 2 experiments. One is Sensei, and the other one is DAMIC-M, that uses the same technology, the same detectors. And both efforts have been in the order of gram scales, okay? A few sensors there. The next thing that is coming is Oscura, that it's a super big jump ahead. Sorry, there is an intermediate thing that is coming. DAMIC-M actually will have a kilogram scale detector, okay? So far, the results that have been published are in the scale of a few grams, but the goal of the DAMIC-M experiment is to have within a few years a kilogram scale detector. So that is the intermediate jump that we are doing, but this is what's coming in the longer term. That is a 10 kilogram experiment with thousands of CCDs together. So this is more like LHC-like effort in which you have to go to a production mode and fabricate a ton of detectors and have thousands of channels and multiplex that and read out everything. Here is one of the modules, the prototype modules with 16 detectors, 16 CCDs in one single module. And Anna has been also working a lot on this, so ask Anna about Oscura if you are interested. Okay, and that's it. I leave you with this to vote or send suggestions for tomorrow if there is something I didn't discuss that you would like me to discuss. And if you have any questions, I'm done.
Okay.
Hello.
Hey.
So, thank you for your talk. I like have two questions. One is, what is the minimum mass of the dark matter candidate for light dark matter that you can like get with silicon detectors like CCDs or so, and how the threshold of your detector affect this minimum limit of the mass of the dark matter? Could you explain me a little bit more?
Yes, sure. So let me go back to this plot. So there are two situations. So if you are looking for scattering events, okay, interactions or candidates that will produce a scattering of an electron but not be fully absorbed, the limit here is essentially close to the mass of one electron. After that, if you go to much lighter, the kinematics are just not matching. Very similar to what you have with WIMPs and very light masses, okay? So here is essentially, back of the envelope estimation. You can say the electron mass is the lowest that you can go, okay? For scattering searches. For full absorption, you can go much, much lower masses, okay? This is essentially, you can go to the silicon band gap, okay? So here, you see, this is EV, okay, in the axis. So you can go essentially to 1 or 1-ish EV. Below that, even if you convert the full mass of the particle into energy, you don't have enough to promote one electron.
And how does the threshold of your detector, like if my threshold is 2 electrons, I cannot see this mass?
If your threshold is 2 electrons, then the calculation becomes a little bit harder, but it's something that we can do and we can measure also. The thing is that at least, I mean, for a threshold of 2 electrons, you would need to have an energy deposition of, at minimum, 2 band gaps, okay? In practice, you usually need more than 2 band gaps because you have a high probability of some of this energy going into heat, going into phonons. So typically you need, on average, more energy to produce that. But we can do that calculation, and we have the distributions for what's the likelihood of producing 2 electrons for a certain amount of energy deposited in the CCD. But yeah, these things are distributions and move up. But the very, very minimum is 2 band gaps or 3 band gaps, depending on your threshold. Thank you.
Okay. When you showed us the table containing the number of events we have on Sensei at Snow Lab,
yes.
They're saying that we had 30 events with 2 electrons, for example.
Yes, and
my question is, this number, the 30, the 2, and the 0, they are already counting other possible sources of these 2, 3, or 4 electrons, or these are all the events you saw containing even background events?
Yep. So for these 32 electron events, actually we have an explanation for all of them. What we have, as I told you before, we have the lowest dark count ever, but there is some dark counts. So the single electron rate is something that it's happening, okay? And just by chance probability, you have some very small but non-zero probability of having 2 single electron events happening next to each other or in the same pixel, okay, during one of these exposures. And when that happens, you create a 2 electron event, okay? And we can compute what is the chance probability of that happening and how many do we expect for the full exposure that we have. And actually that gives us a number that is compatible with 30. So what we understand or what we believe is that these 32 electron events are actually coming from just single electron event coincidences from dark counts. including spurious charge, light from the amplifier, and intrinsic dark counts. So we are not that worried about this. And this number should go down now that we have improved our dark counts. When we produced this result, the dark count rate was 1 order of magnitude higher, so 10 to the minus 4, 20 years instead of 200, so still pretty good, but now it's 1 order of magnitude better, and then you get that this coincidence probability is going down. For the these 2 events with 3 electrons in them, actually this is not compatible with just random coincidences of 1 electron events by a lot. You would expect almost, something that is 0 there, 10 to the minus 7, whatever. I don't remember the number, but it's very, very small. And these 2 events, we cannot explain them as random coincidences. They can still come from environmental radiation. They could be dark matter. But we are not in any way saying that this is dark matter. Okay, I'm just saying this for, yes, we don't know what they are. We are trying to understand that, and hopefully, with a larger data sample, with lower dark count rates, we will understand that better. Yes? Crosstalk? So you mean electronic crosstalk between? Yeah, so no. So to get to this, we did a lot of selection. So all the searches that we do are blind searches. So we take some data that is unblinded, we develop quality cuts on that, and then we run those without modification in a blinded data set. But to get to this cleanliness level, I didn't go in detail, but there are other detector effects, problem. Sometimes you have what we call bleeding, that if you have a lot of charge in 1 pixel, this wave-like movement of the charge is not perfect, and you may leave things behind, so you have to mask some of these things. You also have regions that have defects in the CCDs, and you have to mask them. But these 2 events, with 2 it's very hard to say something, but they appear to be uniformly distributed in time and space. But it's only 2, so we don't know. But regarding crosstalk, I don't know if that was your question, but crosstalk, it's a thing, but we do mask for crosstalk. For example, if we have a very large event that deposits a lot of charge in one section of the CCD, because you are reading the pixels all at the same time in the different parts of this, or the different sensors, sometimes you can have electronic crosstalk. So whenever we have an event in one, we mask whatever is happening in the others. Because there are so few events, that's not really a big hit in efficiency.
So thanks for the nice talk. Maybe a very naive question, but why are the exposures different for each kind of number of electrons in events?
Yeah, because in here, we are using slightly different selection cuts, okay, for the different channels. They are similar, but not the same, okay? Because as I mentioned before, for 2 electrons together, the chance probability is relatively high, okay? So you really want to mask regions in which, for example, you have a slightly higher 1 electron rate, dark current. But then for the 3 and plus, you can be more relaxed about that, because having a 3-fold coincidence, it's much less likely, so you can relax this and also accept regions of the CCDs that have slightly higher dark counts.
Let's see, thank you.
Javier?
Yep.
Thanks for your lecture. I didn't quite get the relation between the first question you proposed us, between threshold and the mass of your sensor, because for me it wasn't obvious the upper the upper side of a big detector? Because in my head was like, it's obviously the smaller one, you spend less in building your detector, it has a smaller threshold. So what will be the advantage of building a big detector?
A bigger detector?
Yeah.
So, I mean, ideally you always want more mass. I mean, that is for true. So if you have 0 background, let's say, you will want to scale up the amount of target material just to be able to access more. I mean, if that doesn't affect your threshold, it will go, I mean, the strength of your limit will grow with the amount of target material that you have. That's for sure. But also, what I'm showing you here a candidate of 10 MeV. If you start going to higher and higher masses, okay, that's not the goal of Sensei, but let's say that you go to 200 MeV or closer to the GeV scale. So this spectrum changes and becomes more extended towards higher energies and ionization numbers. So if you are focusing on things that have a mass that is in the order of hundreds of MeV, then maybe having a threshold of 8 is not as terrible because you still can catch a big fraction of the signal. But that's I mean, depending on what you are aiming for.
Okay, so it would just extend the range of your mass search?
Yes, also.
Okay, okay, thank you.
But I mean, I think that probably for those ranges, it's very hard to compete with the liquid argon or xenon detectors.
Okay, thank you, Javier, very much. We would We would also like to invite Dan and Luca to join the general discussion session, but before that, we have an announcement.
Well, okay. I intended to do this announcement after, but yes, no problem. We can no problem. So 2 announcements. So one is, again, if you're taking the Uber, people that have taken Ubers during the previous days, just send me the receipt so we get to reimburse you, and today the same. And also, so you remember last week we had these practical sessions, and some of them had exercises, for example, to compute the abundances of dark matter generated during early universe and so on. And we said, we'll pay you a beer if you get it right and you show us. And some people did, but we forgot who was. So we decided to pay a beer to everyone, okay? So tomorrow we'll have an informal gathering at 8 in the bar in front of the hotel, so the Garotinha bar. We like it because it sounds carioca. So we have, like, the first beer is on us, and we have very little things to eat also, so that we can, talk to each other. Afterwards, everyone can do whatever they want, including staying there, and but that's it. So we have everyone, we gather at 8 at the Garotinha, and yes, let's have a bit of relaxing time. That were the announcements. Thanks.